Hello, hello. Everything okay? Everything all set here? He's here, so everything should be fine. Assuming this is the GPU. Oh, Geese not doesn't have his sound on, so I don't know. Back. Hello, hello, hello. Everything all set to go here? Daniel? And last minute coffee or don't have the mute off? Daniel, are you back at the desk? Yeah. Okay, for those of you that have that may be sharing notes, I put in a link inside the shared notes of the matrix link so that you can do the chat and do the notes, because you can't do it both on the window. If you click on chat, it will remove the notes, and if you click on share notes, it'll remove the chat. So if you want both, I would go to that link in another window browser, have that up. That way you can keep the shared notes, only for those that want to participate in keeping notes for the track. I will be asking for a write-up at the end of this. Can you get off mute?
Yeah, hi.
Okay. Yeah, I just want to make sure everything's all set. You have all your slides, everything uploaded?
Almost, although could you please check your email for what I just sent you?
Ah.
Thanks.
Let's see. Ah. Can you make him not your first presenter? That's gotta go to Elena.
Yeah, it's impressive. I've sent out a couple of pings, but I suspect everyone's still waking up so far.
Yes. Okay, but since it starts in 1 minute, I don't think we'll have this done in 1 minute. So
Okay.
if we could shuffle around the micro conferences a little bit,
Yep.
hopefully, if it's your first presenter.
Yep. No problem.
Okay, make sure you click the download link on the presenter. Presenter anyway, unless it was Guy wasn't uploading it, was it?
Yeah, that's Guy who's got the.
Well, I just made you presenter, so.
Oh, thank you. Okay, give me.
You're a moderator, so you could give presenter off to anyone.
Yep.
Well, hopefully Guy will be back and be help you. I'm sure he's pretty busy too, so I gotta run off.
Okay, thanks, Steve.
Okay. Yep.
Okay, it's 3:01. As you might have heard from Steve and I talking, we're having a bit of account troubles with Rob, who is supposed to be our first presentation. So we're trying to sort that out now, so we can have Rob join, or very possibly take in as a backup some of the C groups discussion that had happened in Android, but is kind of overflowing into GPUs, since we're talking about memory allocation, memory accounting for GPU memory allocation, as well as runtime accounting for GPU execution. So if you can bear with us for a few minutes whilst we do some urgent behind the scenes flailing, we'll be with you very soon. Thanks. Hi everyone. If you've just joined for the GPU microconference and wondering why you're still looking at the introductory slide, we've had some account issues with Rob, who's supposed to be our first presenter. He hasn't been able to join us yet, so we're trying to arrange a backup with some frantic behind the scenes pings. Hopefully we should hear some more about that in the next couple of minutes, I'm hoping. And we should be able to get started then. Thanks for bearing with us. All right, thanks very much for bearing with us. We appear to have it been sorted by Rob, in fact, being me as well. Okay, so just to do some housekeeping to get us started. Yeah, welcome to the GPU and all kinds of hardware accelerator microconference. Last but not least of Plumbers this week. And just as some housekeeping, of course, thanks to all of the organizers and the speakers as well for all of their time and making this possible, to you for joining, to all of the sponsors of LPC, Facebook, IBM, Microsoft, AWS, Netflix, Red Hat, Collabora, VMware, and the LF for providing all the services as well. LPC is, of course, subject to the code of conduct as well. So please make sure you've read the anti-harassment policy, behave yourself accordingly. And if you do have any issues, please feel free to contact either myself on Matrix or the organizers, and of course we'll do what we can. So to join in the conversation, because this is meant to be more of a workshop style event, please feel free to join the audio conference, but we're all used to by now, please mute yourself when it makes sense. If there's anything you want to ask or anything you're interested in, please chime in either interactively through the audio or through the Matrix chat that we have as well. You can get to that by selecting the chat option in the left-hand side. Yeah, again, thanks to all of the organisers and the committee. We're not on a break. But yeah, so we'll be starting today with Rob Clark, aka Daniel Stone, has been working on some work with DMA Fence for deadline awareness and priority boosting, and a lot of that informed by his work with Fredrino. So Rob, I will drop my screen and I can give you the floor as well. Yep.
Okay, so what do I do to share the presentation? I'm still figuring out this UI thing.
On the bottom part of the screen where you've got the mute, etc. buttons, there's a monitor icon on the right. Actually, there's a
take presenter.
Yep, do that.
All right.
And you should be able to share from there.
So does this work? Can you see? Hopefully.
Not yet.
Okay. I suppose if you want, you can try sharing the slides.
Yeah, I was just doing that in the background, in fact. Present. Magic pipewire, right? Just
there we
yell
go.
at the other me when you need to move it forward.
All right. Well, hi everyone. I'm here to talk about some work I've been doing on teaching DMA Fence about deadlines. So you can go to the next slide if you want. So first, a quick primer on fences. I'll just run through this quickly, but most of the rest of this might not make sense without. A fence context is simply an ordered timeline, and such as a GPU ring. And a fence is a point on an ordered timeline, basically a sequence number. So fence 124 will not be signaled before fence 123 or after fence 125. It's an ordered timeline. A typical implementation for a GPU is simply the hardware writing back a sequence number to some location in memory that the CPU can read after all work on that timeline prior to the fence has completed, and then possibly triggers a interrupt to the CPU if there's something waiting for the fence. So next slide. So one of the first goal, and the first thing that motivated me for this was to close the loop between the GPU's frequency governor and VBlank. Normally, GPU's frequency governor is based on how much of the time it's busy. It's a utilization-based governor. It's trying to solve the problem of what's the minimum frequency to maintain the maximum FPS, basically. But this approach can get stuck at a sort of local maximum instead of a global maximum. I mean, if you think of it, if it's trying to solve a problem, if it gets stuck at 30 FPS and sees idle time because the GPU is waiting, missed a VBlank and is waiting for the next one, that will signal it to reduce the frequency, when in fact you actually want to be increasing the frequency to get to 60 FPS. So next slide. So in this example here, this is a double buffering use case. And if I use numbers in various places, I'm just assuming 60 FPS or 60 Hertz because that's the most common frame rate. But it all extends to 90 or 120 Hertz. But the important thing about VBlank is for most sorts of displays, you only get one chance every 16 milliseconds to put a new frame on the screen. And if you miss that deadline, you're waiting for the next one. So at the bottom here, you can see, these two colors represent the two buffers and double buffering. The below shows the frame being rendered and just slightly missing the VBlank deadline, which extends the time of the previous frame on screen until the next deadline. And the frequency governor sees a bunch of idle time and misinterprets that. We go to the next. So the idea here is when you've queued up the atomic update or page flip, now we know when we'd really like the GPU to be done and signal offense, because VBlank is very predictable. It happens every 16 milliseconds or whatever. So yep, back one. So the idea is to set a deadline on the fence, which propagates through to the driver. And the driver, the GPU driver can set a timer shortly before the deadline. If it sees it's still busy, it can boost the frequency. The idea is to eventually get over that 30 FPS to 60 FPS cliff. And so, okay, now you can go to the next slide. And this is kind of a semi-related case. In this case, there's actually a game that's limiting itself for other reasons to 30 FPS. But at the bottom bar, you can see the GPU utilization, which is shown as relative to the maximum frequency. So you're basically just looking at 0 versus non-zero. And you can see the frequencies jumping around wildly. When the frequency is high enough, we're rendering a frame in 16 milliseconds. But a lot of the time, because of the stalling, the frequency ramps down and we take 2 or 3 times as long. So the end result here is we're jumping between, the frame timing is alternating between 16 milliseconds and 48 milliseconds, which is kind of jittery. Okay, you can go to the next slide now. And then one of the other, back one more, yeah. And then one of the other goals here is more interactive use cases, like say you're sitting there reading a web page and then suddenly you want to scroll down further, or the window switcher animation. In this case, the GPU has been idle for a while. Something happens, and all of a sudden it's really busy. And this can sometimes take an interactive, a utilization-based governor a little while to react to. And so the same thing here. The idea is when the next upcoming page flip is, when you want to be done rendering by. This gives an extra signal to the GPU that someone's waiting for it, and it should ramp up. Okay, and I'm running through this kind of fast, but stop me if anyone has questions. So anyways, the solution here is to add a new method on the DMA fence set deadline. This can, it's not necessarily specific to VBlank, but VBlank's an obvious place where you'd want to use this. So in my patch set, I had a call from DRM Atomic helper wait for fences. And I guess I should mention I-915 does something similar internally where it boosts the GPU frequency based on page flip. Although I think that moved around last time I looked. Anyways, the deadline you set gets propagated through DMA fence array, DMA fence chain, so forth. And eventually gets to the fence context, the fence implementation. If it's a fence exported by the GPU driver, it ends up there. So the fence implementation should track the nearest upcoming deadline, set up a timer for, hand wavy few milliseconds before that deadline. And if the fence isn't signaled by that point, that's a signal to boost the frequency and hurry up. And some other nice things about this is this works perfectly well for cases where you have a separate KMS and render node, render only driver. And it works with all the DRM atomic helpers. And I guess next slide. And a few remaining things to do. Daniel Vetter had wanted to also tie this into DRM scheduler priority. So we can, when you have more complex use cases, say you have multiple applications using the GPU at once, but only one of them is on screen. Maybe you want to give priority to the thing that the page flip is waiting for. And the other issue is some compositors actually defer the decision about whether to flip to the new frame for an application until closer to VBlank, and then they'll decide to re-render either with the new frame or the old frame, depending on whether the new frame is going to be ready in time. So for this, we'll need a DMA fence FDI octal to set so the user space compositor can be the one setting the deadline on the fence. And yeah, and then so far I haven't done too much experimentation with tuning, like how soon before the deadline should we wake up and decide to boost and so on. But yeah, maybe there's maybe there's some room for some knobs so that user space can tune this for different use cases. And yeah, that's it. I ran through it kind of quick, but if anyone has questions, then fire away.
Should we directly then jump into the timing thing too? Because it's practical at the same topic.
Yeah,
Jump into the discussion.
3 Daniels. Amazing.
Yeah, we need more Daniels here. There's not enough.
Yeah, it's definitely related. So like I said, on Matrix, some of the cgroup stuff came out of Android that they didn't get time to finish. So they'll be taking over the presentation time slot up next, just because, I think, to be fair, a lot of presentation time, at least the interesting part, is essentially falling out of the but yeah, I think my main question is, yeah, we would definitely need to be able to inject a deadline so we can be able to speculatively use it rather than commit and then only have it work backwards from there. But have you thought much about the opposite direction when you deliberately want to slow clients and drop GPU usage? Like if you're hitting more of a 40 frames per second cadence and you actually want to slow that so it's closer to 30?
I have not so much. Most of my problems are not going fast enough rather than going too fast. I think if you're not actually able to hit 30 FPS though, and you have like say, and you're only using double buffering, or you have something that's going to stall the pipeline, the simple on demand is going to arrive there. It's, you know, it's looking at how much time you're busy versus how much time you're idle, and trying to come to the minimum frequency where you're never idle, if that makes sense.
Yeah, I would say the same. Like essentially the boosting is just, instead of us approaching like the ideal steady state from below and maybe not getting there because of feedback loops, we're approaching it from above. And I can't think of like a case where we would be stuck at a higher frequency than ideal steady state. Or like what's the use case you have in mind? One of the other Daniels, I mean. I mean, like in a way, if yeah, like Rob said, well, maybe even not just like the busyness, but if we constantly hitting all the deadlines that we're getting, then we know we have headroom, and so the driver could be quite a bit more aggressive. Of course, like eventually we then stop hitting the deadline, and then we know like we've been a bit too far, and we can go back.
Yeah, I mean there are plenty of sysfs knobs for DevFreak. So if user space, you know, wants to set a policy, it can limit the maximum frequency. I mean, there's actually even a user space governor where the user space can just directly control the frequency, although that's not what we use.
Do you know for Android how this works with Swappy and Choreographer? Do the implementations of those have their own similar working backwards from deadline and boost accordingly, or?
So at least on the Snapdragon side, the Qualcomm vendor kernel has some magic trust zone based GPU freak governor. So magic.
Ooh.
You know, because you know you got to use trust zone for that.
Is that trust zone as the patent box, or?
Yeah, I think that's my interpretation.
Yeah. Well, I thought so. I mean, I thought we have a bunch of Android people here, but I thought like on Android it works by immediately boosting when you get the first touch, at least for the interactive case.
That's true. Okay, yeah, this is the part I didn't get around to writing slides to. Even in Chrome OS, we have input handler both for CPU, boosting the CPU on input, and on the GPU side, we don't actually use it for boosting the frequency, but just use it as an early, hey, we should wake up the GPU now, because it takes about a millisecond and a half to boot up the GPU from suspend. And you know that's a thing you don't want to have in your critical path. There's a slight problem in that it works great for touch input, because touch input is touch input. Keyboard input, on the CPU side, there is a cooldown period. So after it boosts, it will not boost again on another input for a certain amount of time to basically, you know, it's the avoid the spacebar heater mechanism. The problem is when you have a keyboard, certain keys you want to handle on press and other keys you want to handle on depress. You know, like modifier keys you want to handle when they're released, because when they're pressed, you don't know what other key is going to go along with it. And the kernel doesn't really have that sort of information, what your keyboard layout is,
And you really don't want it to.
Yeah, is the caps lock key actually a search key or not, so I think what we're going to try and do, but I think no one's had time to like actually do this yet, is move that to user space, and have a user space thing that's kind of sniffing the input events. And like I said earlier, you have enough sysfs knobs to control everything from user space that would be done in the kernel.
I mean, your compositor's already sniffing all of the input because it has to route it, right? So I guess, yeah, in terms of the FD to set the deadline for events, what's the privilege model for that? Is it just you can always set it, or?
This is, it's something we kind of still need to sort out. The last iteration of my series added an ioctl because I needed something for IGT tests to use. Other Daniel didn't like that yet. I don't know if it's, I mean, one approach is you can just say, okay, yeah, if you have the fence FD, you are important enough to set the deadline.
Yeah, I mean,
So
I guess if you have the fence FD, then you're sort of implicitly trusted, and
Right.
if you're the one submitting the work, then you can just spam the GPU to death anyway. So it's kind of a dumb question now. I listen to myself say it out loud.
So I was only complaining about like the lack of real user space in form of a compositor.
Yeah, okay, fair.
I think the interface itself is good. Like any abuse potential is, I mean, you can already like just launch a busy loop on the CPU and burn it. Same on the GPU. But like that's the C group's discussion. And for everything else, like as long as there's like a cooldown so that you can't like you abuse this to get constantly higher priority than the compositor or something, I don't see like an issue.
Yeah, I mean, I didn't really get into the priority part yet because for our use cases, it's usually kind of simple. I mean, you have the GPU process, which is doing everything, compositing and all the rendering and stuff. So, everything's just kind of already FIFO and it doesn't matter so much. But
I guess with Android games, like they can get ahead, can't they, of the next frame?
True. But I mean, yeah, usually the cases where you care, it ends up being a full screen game anyways. So,
So there's nothing else going on with rendering, right?
Yeah.
Well, not the compositor and like the game. Oh,
yeah,
how's this?
you do end up with little pop-ups and things like that. But yeah, it's yeah. I mean, usually you're going directly to the overlay. Let's say.
Yeah, I mean, I guess when it comes to plumbing it through to scheduler, if you want to have a prioritized compositor, then you already have to have context priorities. So maybe one thing for the fence deadline is rather than a pure fence ioctl, like at the moment you work backwards from commit in KMS, right? And you sort of plumb that back. And maybe the model for boosting from a compositor use case is to similarly push it through a DRM context. So empty batch with a dependency on that or something like that.
I mean, it's still that the actual rendering happens in the other context from the app.
Yeah, but then
So it still needs to go through the fences. I mean, honestly, I'm not worried about the priority stuff because it sounds like for Chrome OS right now it's not a problem. We have plans to cut i915 over to DRM scheduler. And as part of that, we need to cut it over to this DRM fence set deadline stuff because
Yeah, I mean,
the things we have are too clever.
yeah, what needs to be done is not, I think, too hard. I just need to think through how to implement it. But at some point, this scheduler is going to be waiting on a fence to know that it can schedule some other job, right? Because it's not, it's deferring writing jobs into the ring, with its own scheduling, which is based on waiting on a fence. So we need to propagate from that fence to the actual hardware fence what the deadline is.
Yeah, but I thought that part you have already. Oh, you mean like the dependency propagate? Oh,
I mean, when the scheduler itself is waiting on a fence to schedule another job.
yeah, but for just clock boosting, it doesn't matter because as long as you boost one and you only have one GPU, which I think is your case, it's all fine. And honest, so for me, it would be perfectly fine if we offload the priority boosting and dependency boosting to when i915 people need to do the conversion.
Yeah, I mean,
Like,
I think that the point I was trying to get at is the DRM scheduler fence doesn't actually propagate the deadline to the hardware fence until it has a hardware fence. So in the case that it doesn't have one yet,
oh right, yeah,
it needs to
I
be
guess
propagated.
you do miss it.
Right.
Yeah, so as I understand it, you're directly boosting in the GPU driver when you're hitting the deadline. I wonder if we could maybe offload some of that to the DRM scheduler. So also keep a history of missed fences or something like that on the run queue where those jobs are showing up, because right now you're always working backwards from missed fences and then directly boosting the GPU. But if one of those processes is idle for some period of time, you probably want to have some history of how heavy is this run queue on the GPU, and then if it gets active again because user space starts to submit jobs again, you really want to boost up the GPU at that time if you already know that the run queue is going to be heavy.
Yeah, I mean, this is part of the reason. I mean, my initial idea was more reactive and giving this driver a signal that it's missed frames, but I think the better idea is to boost before you miss the first frame in the first place, and that's the idea. I mean, that's why the implementation sets a timer a few milliseconds before vblank. Yeah, I mean, if you have a case where the workload's varying a lot, like it's not doing something for a while and then it starts an animation or something, that's kind of hard to predict.
Yeah, that's more the like the going from idle to not idle, and what we do in i950 is we just kick it. And I think it keeps track, maybe it even keeps track of like a per context history of what was the last frequency, like steady state. And then yeah, if you scroll the next paragraph down on your browser or whatever, like it just kicks you back to whatever it was, half frequency or full.
Yeah.
At the moment you submit the first thing.
Yeah, so the recent dev freak changes on the DRM MSM side actually do a combination of things. Like if you've been idle for a long period relative to the sampling interval, it will give you some boost initially. For example, I mean, it's kind of analogous to the input boost.
I think the thing to avoid maybe is going full i915 and trying to like i915 tracks this all on every single job, and with priority inheritance and kicking it all out, and that's overkill in my opinion.
Yeah.
Like a bit of boosting on like the context priority temporarily or whatever for the dependency, that kind of stuff. Or what Lucas said, tracking a bit of like histogram maybe might be useful. So you know, okay, this thing is coming in, I need to crank it back up to like full speed right away. And not so fancy.
Yeah, can you guys hear me now?
Yeah.
Ah, great. Yeah, I had some problems with the microphone. Christian here. Yeah, basically what you talk about the scheduler and the backend hardware driver is not informed about the deadline until the job is actually scheduled on the hardware. It's, I think, a general problem which I noticed in this concept before. Basically, when we submit something to the hardware, when we submit the flip, the deadline will be set on the last DMA buff, last DMA fence instance. The problem is now that a picture or the flip can be composed by multiple engines all over the GPU. It could be part of the 3D pipeline, it could be part of compute, and it could be part of the SDMA or the multimedia engines, like decoding or encoding or stuff like that. And at least for AMD hardware, what will happen is that when you boost the last fence, which is most likely the one just drawing the picture on the screen, you're actually not hitting the right engine. And for example, for video decoding, when you say, okay, I should be decoding at 60 FPS or something like that, but I'm only decoding at 30 or 45 or whatever, we would need to propagate that from the 3D engine, which currently does the color space conversion, back to the UVD engine or VCN engine, which does the decoding for things like things like transcription. I'm not sure if working with the end of the pipeline is the right approach here.
So I take it the kernel is managing frequencies for all the different blocks in the GPU individually in your case?
Yeah.
Okay. Yeah. I mean, that's, the situation is a little simpler for us. I mean, video decode is actually even a completely separate subsystem in the kernel for us. And we just have one top level frequency, and then the GMU firmware can do more fine-grained things internally in the GPU. But I guess if you have multiple different frequencies, you need to wait to understand that dependency chain.
Yeah, probably. I mean, the alternative would be, to say, okay, we are not signaling the fence, but we are signaling the hardware which issued the fence or the context or something like that. But I don't really see how we should do this, especially when we say we have inter-device dependencies. Like you said, you could have one device which does the color space conversion, and completely different driver on a different device, which does does decoding or things like scaling or drawing and stuff like that. And at least for the scheduler, what you essentially need, I think, is that you not propagate the deadline to the hardware fence, because that's way too late, but whether to the dependencies of a job. So when you set a deadline and you see, okay, I am waiting currently on fence whatever, then propagate this deadline to this fence and not to the hardware fence. I think that would at least be a start of solving this problem.
Yeah, I think
well,
that's. Sorry.
Go ahead.
Yeah, I think that's essentially what we need to do there for like more complex hardware that isn't just a single clock domain. And I think we can. The priority boosting has kind of the same problem. Like, there's no point if you're boosting the last one if all the other ones are still hung up. Yeah. So honestly, like this problem use case is part of the motivation why I wanted to lift the dependency tracking into the DRM scheduler, so we could start doing these kind of things.
So
and maybe aside for Christian, I do have like some ideas how I could get this rolled out for AMD2. I just didn't get around to it yet. So I think we should be happy here.
Quick admin note. We've got like 2 minutes, and then we should switch over to Frigid talking us through cgroups. So whoever wants to get the last word in, if that's you, Jason or Christian.
I was just going to comment that, particularly if you're dealing with dependency chains that are any longer than just 3D rendering and displaying it, you also have a problem of figuring out sort of how to allocate time to each of the different jobs in the chain so that you can create all of those fence deadlines. And if the different drivers are allocating time independently, then they all have their own feedback loops, and those feedback loops are going to start fighting with each other, and you're never going to get to a competent steady state. So it makes perfect sense if you've got, a game running full screen displaying. That case is pretty obvious how it works, but once you get the pipeline any deeper than that, I'm really confused as to how this is actually going to hit steady state without maybe something central like DRM scheduler keeping track of things and handing out time slices. Maybe that is
I
the
think
answer.
that's essentially the entire presentation headache, presentation timing headache, because I think discussions on that have been ongoing for like 3 years by now. So maybe we need to resurrect Daniel Stone's topic for after C groups or something like that, so we can appreciate the frustration that this topic brings in.
Yeah, but I mean, that one's kind of been stalled in the horrible chicken and egg of we don't have higher level APIs to design against because clients don't really care about them too much because it's not plumbed down at the low end and no one knows anything of what's going on apart from it's really hard and it's not being solved end to end at the moment.
Yeah, so I mean, this is why I think we should just go ahead with what Rob has now, fully aware that there's endless amounts of holes and we just need to plug them as we go and create funny, unstable feedback loops and then figure out how to solve them, because I think just talking about the problem has proven itself to be not useful.
Yeah, I think we are in danger of trying to boil the ocean if we try to tie everything in and get it completely complete from the start. So yeah, definitely in favor of doing it wrong and finding out. Cool.
Start somewhere.
Sorry?
I said you got to start somewhere.
Yeah, exactly.
Yeah.
Cool. All right. Yeah, on that note, thanks Rob/me and other Daniel and Christian and Jason and Lucas and everyone. So yeah, that'll be fun. The patches are out on DRI Devel, so go have a look if you're interested, and yeah, have fun with feedback loops.
Yeah, I should hopefully have another iteration. Well, I didn't get to it this week, so hopefully next week. All right.
Nice. Okay, so Phrygia and John and some others, anyone else who wants to join from the Android side. There were some discussions ongoing out of the Android microconf about C groups and how to allocate for device memory allocations and usage. So Hridya, if you want to take it away, I've made you presenter, so you should be able to share anything.
Hi, Daniel. Thank you. Yeah, we had a brief talk in the Android MC on evaluating the GPU C groups for adoption in Android, and yeah, we thought it would be great if we could also have a discussion here, so we could know what you thought of regarding our proposals and whether you had any other ideas for us to try out. Daniel, would you like me to quickly run through the slides again, just to catch everyone up to where we ended in the Android microconference?
Yeah, I think that's good. I think there's a lot of people here who weren't there yesterday, so thanks.
Okay. Okay, sounds good. The presentation is about a new memory accounting feature that we are looking into for looking for implementing into Android. And over the next few slides, I can walk you through the various solutions we explored to implement the same. Yeah, at the end, hopefully we can have a discussion on the next step forward. So the problems that we are trying to solve are that currently there is no way to limit the total amount of DMA of memory allocated on behalf of a process. This means that right now, a malicious or a faulty process can continue allocating DMA of memory until the device falls under memory pressure. Similarly, origins of a buffer leak are also hard to identify. So when we find a leaked DMA of FD held by a process, due to the shareable nature of DMA of FDs, sometimes we find it hard to identify why the buffer was allocated in the first place. So these are the problems that we are trying to solve. We would like to know why a DMA buff came into being, and we would also like to limit, set an upper limit on the total amount of DMA of memory allocated on behalf of a process. So we explored a few different solutions, and in the next few slides, I can give you a quick overview of our analysis. So the first solution we looked into was the MEMCG controller. The problem we had with the memory C group controller was that Android uses a per app C group hierarchy. So when we evaluated enabling MEMCG with the per app C group hierarchy that Android is currently using, there was a noticeable overhead on some use cases, and which meant that not all Android partners were on board with enabling the memory controller C group with the per process C group hierarchy in Android. So yeah, we just didn't have all Android partners on board with enabling MEMCG. So it might not be the solution that we are hoping for in this case, because we would like a solution that would work for all our partners. Additionally, MEMCG performs accounting in units of page. As you know, in the DMA buffer sharing model, a process takes a reference to the entire buffer, hence keeping it alive even if it is only accessing parts of it. So the per page memory tracking feels like an unnecessary overhead for DMA memory accounting. More importantly, there is actually no need to use C groups to track which processes are holding FD or map references to a DMA buff, because we already have this information available from ProcFS. So for our use case of allocator attribution for DMA buffs, we feel like the memory C group controller might not be the best way forward. So the next solution we looked at was whether we can use a user space service to keep track of buffer allocations and releases. However, we could not find a sure shot way to intercept that, to ensure that a user space service can intercept all DMA buff allocations and releases. This is because DMA buff allocation in Android happens through the DMA buff heap ioctils, and the buffer release, of course, happens when the last reference to the buffer has been dropped. So yeah, basically there is no way for us to guarantee that the user space service would intercept all allocations and releases, and this is very important for our use case of setting an upper limit on how much DMA buff memory can be allocated on behalf of a process. Additionally, this was also important to us in case the user space service aggregating this data got killed or restarted for some reason, we would lose all accounting so far. So until the device reboots, we wouldn't have the service available. We wouldn't have an effective tracking available. We looked into the GPU C group controller that is already under construction upstream. And yeah, it looked like a good fit for what we wanted to do. And Daniel V has also been encouraging us to evaluate for Android for some time now. So we did that. And over the next few slides, I can walk you over what we found out. So since the GPU C group controller is actually originally intended to be used by the upstream GPU drivers, the API from the latest RFC is closely tied to the DRM framework. If the original authors of the C group controller are okay with doing so, and they don't have an issue with doing so, obviously, it should be easy enough to ensure to modify the API to be generic, though, ensuring that it still works for DRM while also accommodating use by other DMA buff exporters like DMA buff heaps. So yeah, that is one thing we would need for DMA buff heaps to use the same charge and charge APIs that the GPU C group controller exposes. So the next problem that we have is actually not really specific to the GPU C group controller. It relates more to the way DMA buffs are allocated in Android. So in Android, we have a process called the graphics allocator process, or the gralloc-hal process, which does the majority of DMA buff allocations. So what happens is that a client requests the gralloc-hal process for an allocation over IPC with some specific requirements and constraints. And the gralloc-hal process allocates a DMA buff, following all the requirements that are set by the client. And once this is done, it sends the FD back to the client over IPC, and it does not retain any references to the buffer. So what this means is that if we charge every allocated buffer to the process that allocated it, we are not going to have an effective allocator attribution for DMA buffs in Android, because the gralloc HAL process is going to be on the hook for all allocation, or for the majority of DMA buff allocations in Android. So this is actually a problem for us too. To solve this, we proposed a few different solutions, and I can walk you through all of them really quickly. So the first, we need a way, basically what we need is a way to charge a buffer to the C group of a process other than that of the allocating process. So we need a way to declare that this buffer should be attributed to another C group. So that is the problem that we are trying to solve here. So the first option we looked at was explicit charge migration, that is using the C group interface to move the charge to a charge of a buffer to a different C group. So in this case, that would be, in the case of Android, that would be the client who requested gralloc HAL for allocation. So for example, maybe the allocating process could write the DMA buff FD to a file in the client process C group. However, when we took this up with the C group maintainers, and this actually differs quite a bit from how resource accounting is currently done in C group controllers. So yeah, they didn't really think that this was an upstreamable interface. The next solution that we looked into was maybe to check whether we can come up with a mechanism similar to fadvice don't need, where the allocating process can just declare that it is not going to use the allocated buffer. The buffer will then be charged to the process who accesses it next. So we thought that the results would be really non-deterministic with such a scheme, though, because the process who receives the FD over IPC might not map or install the FD and pass it over to another process straight away. And this means that it would really not work for our use case of setting an upper limit for allocations of processes. So we did not think that this solution would be a good fit for our use case due to it not being as deterministic as we want it to be. So the last option we looked into was whether we can have a new DMA buff heap allocation ioctl that takes as argument an FD to the C group of the client process. So the gralloc HAL process in Android that I talked about, it does know who the client is, who is allocating, who is requesting the allocation, and it will also have information on which would be the C group this process belongs to. So in the ioctl handler, the heap driver would check whether the limit for the allocation limit for the client C group has already been met. If not, it proceeds with the allocation, and if the limit has already been met, it would fail the allocation. So basically the limit checking and charging would happen in the ioctl handler. So to guarantee that SE policy restrictions would guarantee that access to this ioctl would only be provided to approved processes. So in this case, for the case of Android, we would probably only provide the graphics allocator HAL the permission to charge, permission to use the new DMA buff heap allocation ioctl, unless we find other valid use cases. So yeah, these are the various solutions that we looked into to solve this problem. So yeah, if you can think of any other approaches that we can use to find a find a solution to the problem, or if you had any other anything else that any other suggestions that we could look into, yeah, we would be really happy to collaborate. And yeah, it would be nice if we could have a discussion on this.
Great. Thanks a lot for that. Yeah, the comment I had as well when I'd seen the original proposal is we kind of have the reverse problem for generic Linux, right? Where, you know, Android, you have the trusted Grelic service in one process and you need to migrate the charge across from A to B. We've got the opposite problem where the client will be doing the allocation, and anything, you have the same problem with Hardware Composer or Service Flinger, I guess, right? Where anything that's either implicit on processors owning FDs or is explicit with a client saying, charge this allocation over to this other one over here. That, yeah, that wouldn't be great for us, because then the client's just gonna account everything to the compositor. So I think one thing which would actually work for both, if I understand how policies around binder work and what you have for Android, is if the receiving client could essentially adopt or take responsibility for the allocation. So I think that works out because you're able to have a policy of this binder call can only come from this DSO or whatever it is, right? And for us, that would work well too, because the compositor would never say, I want to take responsibility for this allocation.
Sorry, Daniel, I got a little confused. So are you proposing a plan to build this into the binder infrastructure, the binder driver itself, or is it a different scheme?
Yeah, so what I'm suggesting is that all of the suggestions you had involve the process or the component which made the allocation,
Yeah.
transferring the allocation to something else, some
Yeah.
other PID or the other end of the socket, right?
Yes.
What I'm suggesting is the reverse. So whichever process receives the allocation is able to claim responsibility for that.
Oh, okay.
So that works for the generic Linux model, because it's almost always that the allocation is less trusted and the one receiving the FD is more trusted. And I think for Android, that would also be compatible with the security model, because I think you have some way to specify that, like a policy to say that this binder call can only be made from this shared library. So you could enforce that whoever makes the call to Grelic, it was coming from a DSO, which would also adopt the accounting.
So I'm actually, I don't think we can do that, Daniel, because we cannot guarantee which processors would call out to Grelic HAL. So yeah, there is no, we don't have a middle layer where we can set a rule that only known processes can call out to the Grelic HAL. So both these could be vendor process too, and it could be something on the system side too. So yeah, basically we don't have control over limiting who can call out into the Gralloc HAL.
Okay, I thought there was some insanely fancy mechanism where it was like this binder call can only be made from, you know, this code location, right? So you could delegate it to a trusted library, but maybe that was just a nice idea in a conference talk and it never got implemented.
Yeah.
Sorry. Oh, I guess I should. But couldn't we like extend this idea and essentially like when binder or maybe AF Unix or whatever like passes an FD along, we do, or maybe only binder, we do an option where like it kind of closes your file descriptor locally and transfers the resource allocation that is hanging off this FD with a new struct file operations callback, maybe. I'm not sure that it's maybe a bit special, but I mean that's kind of the entire point of having this binder IPC thing. And if we start attaching random C groups and other allocations to FDs, maybe we do want to like formally transfer them, and they
I think we basically have the problem that inside the Linux kernel, all resource management is currently attached to the process and not to the file descriptor. So, for example, you can also just call memfd create and just loop in an endless loop and write bytes into it. And after some time, the out-of-memory killer will just kill PIDs, but never the PID which is actually using the memory.
Yeah.
The core of the problem is that the resource management system doesn't look at file descriptors at all. It just only looks at the resident set size or the shared set size or something like that of the process, but not at files the process has open. And if we could adjust, or if we could come up with a resource management for file descriptors, that would certainly be a start into the right direction to solve those problems, and not only for DMA buff, but also for DRM devices like video devices.
I think we talked about this with Android resource tracking too, because Android has this OOM interface thingy, but I think the problem was that counting at OOM time was too expensive, or something.
Exactly.
I like, and that was also another like reasons why we came up with couldn't we use C groups, because Android already has like the user space OOM killer thingy.
Yeah.
And looking at sorry.
Yeah, the low memory killer daemon that we talked about when we last chatted.
Yeah, and so like tracking all this stuff in C groups and then shooting it with the user space OOM killer is seems like the solid approach here. It does mean that like if your tester doesn't set it up or your OS, then you're still stuck with hilarity. Maybe since this has come up, like the entire how should we interact with memcg question. Honestly, my personal take is since memcg seems to be a problem for Android, and we've historically not tracked any of our allocations there anyway, maybe we should just like continue that and say, and the third reason is all these special pools, even if it is in main memory, like there's the TTM page pool, there's the various ion DMA buff heaps and all these, like I'm leaning to it tracking DMA buffs in like a device or special C groups controller, even if it's like in system memory, and kind of taking it out of memcg. But That's maybe also like a question we have.
I'm not sure if I'm really understanding what the premise here is. Are we talking about like a cgroup controller for controlling all DMA buffs, regardless of which device they're actually coming from? Or are we looking at something more fine-grained where that usage is tracked per device?
I think both. So maybe there's one overall for all the DMA buffs, and then per memory pool, whatever that thing is, could be like VRAM, or like if you have multi GPU, something interconnected, a piece of VRAM maybe. If you have like more a NUMA GPU, or on the Android SOC side, it's like the various CMA heaps in system memory. So that would kind of be split out.
In my mind,
and obviously
DMA
like
buff
just
is not an allocator, it's a buffer sharing mechanism, right? And tracking usage on the buffer sharing mechanism seems kind of weird. I would track it at the level of the allocator where the memory actually comes from.
maybe this is the confusion between Android and Linux, because on Android, DMA buff is the allocator.
Yeah, and Android kind of abuses DMA buff a bit.
So yeah.
Yeah, basically,
It's different.
Android, it's different. That's a bit questionable, but okay, they can do what they want. I mean, basically on Android, each allocated buffer is kept a DMA buff file descriptor handle for. On normally Linux or VM drivers or video for Linux drivers, we only use the DMA buff file descriptor handle as intermediate handle. So what the driver does is exports its buffer, user space gets the file descriptor, imports it on the other side, and the file descriptor is then closed. Android, on the other hand, keeps those file descriptor around for a very, very long time, as long as the buffer exists. Yeah, Felix is generally right that this is maybe not the best design, because you run into file descriptor limitations. The number of file descriptors you can have open is quite limited. I think it's around 1024 by default or something.
It's lifted.
It's lifted. Yeah. Okay.
Yeah. This was
probably
lifted.
outdated my information on that. Anyway, yeah. In general, when we would want to solve the memcg interaction between drivers and memcg, we wouldn't do that on the DMA buff level in general, I think.
So I think it's just naming here. Like for Android, this is the DMA buff C group controller thingy, right? But like in Linux, it wouldn't kick in only when you do the DMA buff export. It would kick in when you allocate from an allocator. It's just on Android, like the allocated port and the export to DMA buff is one thing.
Yeah.
And that's why all the Android people talk about the DMA buff C group controller.
But
it's really like an
allocator,
allocator
right?
C group controller. Sorry.
That's only really true for the display buffers that are shared with the compositor. Like internal allocations in the user mode drivers, I don't think they would use DMA buff.
They
They are
won't.
all going through the Gralog allocator, so they have a central allocator for all the DMA-able memory. So it's all going to one device that's having controlling the DMA buff heaps and then allocating from there. So all the graphics memory is coming from Gralog. So even the driver internal allocations. So yeah, it's really a different world to the general Linux system where you have the allocations scattered around different drivers and then just have DMA buff to glue it all together and transfer handles to those allocations between different drivers, and Android where you have one central instance where all the allocations are happening, and then Gralog is handing out allocations with DMA buff handlers to all the user space components.
Okay. Well, there is an interesting parallel there to Rockham where we have this shared virtual address space across multiple devices, and if we want to share those buffers over peer-to-peer DMA, we'll basically have to export all our buffers as DMA buffs so that we can import them on the other device. And so we have some code in the works for that, where basically all of the VRAM gets exported as DMA buff, so it can be imported on other GPUs. And so we'll heavily depend on the DMA buff move notifier so that we don't lose the ability to evict our VRAM buffers. And so that means basically all memory allocations will be DMA buffers. And so if you overly limit the DMA buff usage, you'll be in trouble. But it sounds like Android is going to be in the same boat. So you basically have to set the limits appropriately to satisfy all the applications memory allocations.
Yeah, I mean, the limit is not like limit on shared buffer, it's limit on like GPU memory allocations.
Okay.
That's
right.
the goal. So,
Then
and I don't think in practice it's going to be a problem because, like, sure, it's called DMA buff cgroup, but like even on Android, it's not in the DMA buff.c file. It's in the DMA buff heaps, which is like the allocator.
Yeah.
And in the DRM subsystem, on like the more Linuxy drivers, we can just smash it into all the allocators because the DMA buff export step does not actually do any accounting. So, but yeah, maybe the patch series or the doc patch should have this in like the intro section about, hey, there's the slight naming confusion between Android and Linux about what things do and how they work.
Yeah, I think what we're really talking about here is device memory allocations, not really DMA buff, but memory that's allocated by a device driver or the ion heaps on behalf of a user space process. So.
Right, and then you're using DMA buff to attribute which process it gets accounted to, right?
No, I don't think the DMA buff framework would need any changes at all for the charging and uncharging mechanisms. For example, like Daniel mentioned, in the case of DMA buff heaps, each of the heap driver would be the one invoking the charge and uncharge API, because the release export operation is also set by the DMA buff exporter, which in this case is the heap driver, right? So there would be no code in the DMA buff framework which relates to charging and uncharging. It would all be done in the exporter side. So for example, the drivers and the DMA buff heaps.
Well, I guess if we go with the binder for the charge transfer thing, maybe binder or DMA, or like maybe there might be something there, so that binder knows, oh, this is like if we do the charge transfer only for DMA buff and not as a struct file operations kind of fully generic interface, then maybe we need to have something there about, hey, please transfer the charge. Thank you. But yeah, otherwise, like this has nothing to do with DMA buff. Oh, by the way, Lucas, the ion heaps are called DMA buff heaps now, just to make the confusion perfect.
Right.
Okay, is anyone?
Yeah, so the one thing I'm wondering about is if we are tracking all this memory in a totally different world, is how this would interact with the general memory accounting in the Linux kernel. So currently, we don't really account graphics buffers at all, even if they're in sysram, and we have all the obvious problems with that, with the wrong processes getting killed if a GPU process is going haywire and allocating memory without touching it from a user space, just with the GPU. And I would really like to, have at least some kind of, road towards solving that problem also, because that's something we really have, hanging around since a few years, and it's not getting, and we are not making any progress on that. So
So
I'm not really sure if just accounting the DMA buff stuff is the right thing to do, and accounting it in a totally different C group. So, yeah.
I mean, this is essentially the MEMCG question, because if we just slap, we'll just slap GFP memalloc over like all our system memory allocations. So even when they go through like CMA or anyway, like by the time they hit the page allocator, if we consistently set the GFP memalloc or whatever, maybe it's called different flag, then all that stuff will be accounted to the kernel memory, system memory usage in the MEMCG controller. And Tejun has brought this up from the C groups maintainer side. The problem is, like, apparently the overhead of enabling this is quite a thing. And it might also be a bit a game of whack-a-mole, because getting the GFP flags so like passed down through all the layers, including DMA, API, and everything, might be a bit entertaining. So my somewhat pragmatic stance here is that we just shrug and keep doing what we've been doing, but it's definitely an open question. Yeah. The other thing is also this wouldn't help anyway where you have special memory pools like CMA, because MEMCG understands user space allocations versus kernel space allocations, but it does not understand, oh, you've run out of like stuff here or there. So even if we fully wire up MEMCG across all GPU drivers, DMA buff heaps, and whatever else there is, we still have a pretty massive gap in the accounting.
Right. So, yeah.
So
Again,
yeah,
we shouldn't try to boil the ocean, right?
Yeah, exactly. So I mean, like if you have a sock with a display that needs contig memory, right? You want to make sure that your compositor can always allocate whatever is there, then you still need a user space OOM killer for your contig memory, and probably still a C group controllers specifically for all the CMA allocations. So yeah. And I'm also like, for the OOM killer, I'm also getting the feeling that the path forward that user space is picking is a user space OOM killer. Like Android has it since forever. I don't know about Chrome OS, maybe someone knows. But yeah, Systemd is rolling out their own OOM killer because like the kernel just doesn't know enough. And so like Android will glue DMA buff C groups into the OOM killer. Like it shouldn't be too hard to do this into Systemd OOM. And that would solve the problem too, I think.
Yeah, then the next complication is devices with local memory. So, what's the limit if you have a device that's having 4 gigs of memory and 4 gigs of VRAM, and do you try to charge the C group when evicting stuff from VRAM and decharging it if you're moving back to VRAM, or how would that work?
So we discussed this a bit, and I think it was Alex Deuker who brought up that there's machines out there with substantially more VRAM in total than system memory. Yep. Like at first I was like, we need to make sure that eviction keeps working. But like, if you have more VRAM than system memory, then eviction is not guaranteed to work. And now I'm leaning towards, if you've misconfigured like your limits and it doesn't work, you just get to keep the pieces. Like, if you have, for example, like, I don't know, a server thing, and you set like the disk, well, not disk, NVMe nowadays, block IO limits to guarantee that your server gets all the memory needs, but then you forget to like give it enough CPU time and it can't actually use it, then it's like, yeah, you just screwed up. So if you set like your VRAM limits stupid and your system RAM limits stupid, so that eviction doesn't work and your workload fails and everything crashes, it's like, it's like, don't do that.
I
So
guess,
I don't think, yeah,
Shooting in your foot is supposed to hurt.
yeah. So
I mean, I guess mirroring what normal anonymous memory does when you swap it out, like there's probably some kind of sense in that. And how far do you go down that rabbit hole in the sense of when you evict to swap, does that also get charged against your block IO quota? Like, you know, there's how deep do you want to go with that, right?
Yeah, I mean,
but speaking of
we have been discussing that also. One requirement which comes up quite often is to have a cgroup controller which controls local device memory, like VRAM on graphics hardware. And the problem with that is people think they can then say, okay, this application should only use maybe 1 gigabyte of video memory. What they don't think about is that the application then won't stop magically using exactly 1 gigabyte of video memory, but they will still allocate more, whatever they need, and you end up with eviction and moving buffers in and out of VRAM. So what you actually want to control is not the amount of VRAM an application uses, but the amount of I/O an application causes. Like how much shuffling of buffers, how much block I/O, like you said, to when we actually do swapping, because an application is running wild and allocating everything it can get, etc. And device memory is basically just like a cage of system memory, I think.
Speaking of exceeding allocations, where we're running up right against our time limit. Is there something anyone wanted to say in conclusion? Or?
So I can follow up on the binder approach that Daniel, you and Daniel, we had talked about. And yeah, I mean, I can reach out to you guys on what should be the next step once I do that. And include Kenny and Brian as well, since they own the GPC groups.
But by the way, for the charging, did you chat with Tejun about this problem? I've never.
Yeah, we had a thread with Tejun about the charging issue, Daniel. So yeah, the first approach that I mentioned, the one using the cgroup interface for explicit charge migration, so he was not okay with that. And yeah, the last approach that we talked about, the using a separate ioctl, that is completely different from the cgroup interface. Yeah, they seemed mildly okay with that, but I will follow up on whether that is going to be okay with the cgroup maintenance.
Yeah, maybe check with them whether the binder-based charge transfer is looking reasonable.
Yeah, definitely. So I'll definitely look into that next. I think that should be the next step for me. Thank you.
Yeah, and to start the bike shedding early, I really do believe that this is not the GPU C group is not the right place to have this memory allocation tracked by, because in a general Linux user space, we really want to hook in other allocators like the video for Linux allocator and stuff like that. So I do not think that GPU memory limit is the right thing to name this, but it's more device memory C group or something like that.
I mean, that's why it was called DMA buff cgroup, but that's also confusing.
Yep.
But yeah, there's a bike shed.
Oh, we'll get there. Okay. Thanks a lot, Fridja and Daniel and Christian and Lucas again and everyone else. It's like we've got some good sheds to paint. Okay, so we now have some of you might welcome this, I know I am, 15-minute break or thereabouts. So after we come back in 12-ish minutes from now, Daniel Phillips and some of the other AMD compute people are going to walk us through HMM and what that means, and stick themselves up for all of the tomatoes we can throw at them, I think.
Yeah, hope to see you there.
Thank you. See you soon. So we've got around 2 minutes until we'll resume at 10 to the hour, 50 past in whatever time zone you are. So yeah, last call for refilling coffee, water, whatever have you.
Who was speaking?
I think that was Daniel Stone.
How's my sound level?
Sounds good to me.
You're very quiet.
Am I using the right microphone?
I'm actually hearing you on the AMD laptop also. So I guess maybe not. Hmm. Okay, that was because I had the YouTube live stream running on the laptop. Would you like to do another sound check, Felix?
Okay, how is this?
It's still quite quiet. Do you have mic volume control?
We're now.
Felix, I hear you okay somehow. I don't find it very feeble. You sounded okay to me.
Yep, and I hear you fine.
Yeah.
Okay, I don't know. I
Okay.
don't see I can change anything. So
It's good enough.
speak louder.
Good enough.
It's workable.
Right.
Okay. Yeah, so hope you all enjoyed the break and catching your breath. You know, I've got some iced tea and Australia's finest baked goods, the Lamington ready. So yeah, Daniel and Felix and a cast of thousands from AMD are going to run us through HMM, HSA, KFD, SVM, various other acronyms I missed in essentially the more compute and less display focused side of the world, and especially how that interacts with the memory manager. So Daniel, were you sharing to kick off?
Yeah,
Or was it Felix?
that was the plan. And how do I address you? Do I say good day?
Any way you like. I mean, I'm about half by this point, so you can say hello if you like.
Hello.
Yeah, so you should have down in the bottom in the tray with your mute button as well. You should have a screen share.
Yeah, I've got a screen share, but we've also got Felix's slides
Okay.
somewhere. Yeah, so can we get those up somehow?
Felix, you can now share if you like.
Oh, okay. Then I think I'm just going to share my screen. That's the easiest way, I think.
Okay, that's fine. Okay, so I'll get started. So here I am on my Ryzen 1700 8-core desktop machine running Debian SID And here we are meeting together on the best and most modern video meeting software in the known universe. And I just have to say, geez, in the 23 years since I started working on the Linux kernel, we've come quite some way. Yeah, back then it was Windows 98 ruling the world. So today we're entering kind of a new world, and part of that is the ascendancy of the GPU, where we have more processing power now on the GPUs by orders of magnitude than we have on even our multi-core CPUs, and more memory too. And that's really something new for the Linux kernel, or relatively new. Maybe not new for Felix, but new for a lot of us. So that's what we're here today about. We are expanding the scope of what Linux kernel can do with GPU memory, and in the process, kind of breaking new ground and defining a model for device memory in general. Although, to be honest, our purpose today here is more specific than that. We want to get a patch set merged, and we want that specifically for migrating device memory. So that's what we're going to try and focus on, but just let me diverge a bit here. And wax poetic about where I think the GPU is going. Well, for one thing, it's what we're doing here is soon going to be part of the world's biggest supercomputer, that is the Frontier supercomputer, and others. So that's the immediate importance, but it's not going to stop there. This kind of device memory sharing between the processor and GPU is going to become part of many different kinds of devices, even cell phones. I can see it. I can see the ascension of the GPU and the cell phone as well. That is computing on the GPU, and sharing of memory is soon. We're all going to have vision processing and AI processing, and we already do to some extent, but we're going to have a lot more of it. And we're going to have things that we don't even know about yet. And we're going to have this kind of thing on our desktops as well. Of course, we already do, but we're going to have more of that again. So yeah, we're kind of nibbling at the corner of something that's going to become much bigger over time. And with that said, I'm going to kind of bring the talk back to the the present universe, and get ready to hand over to Felix. So what we would like to do, the format for today's micro conference, which was going to be a BOF. I'm going to talk for a couple of minutes, and I've just about used that up. And then Felix is going to present the content on the slides, which is designed just to be a few minutes. It was designed to fit a BOF rather than a mini conference. But I'm sure Felix can go on for as long as we have with interesting technical content and war stories. But what we really want to do is we want to meet the people in the room. We want to meet anybody who's interested in this. We are particularly interested in meeting and engaging with people who are in the LKML threads having to do with merging our memory migration for device memory as part of HMM, which we would like to get merged by in the 5.16 kernel if we possibly can. So that's our goal. Okay, so I am just about done with framing that. One more thing. Anybody here should err on the side of turning on their video. I think we've got the bandwidth for that seems to be okay, and err on the side of turning on your sound. And please do introduce yourself the first time we speak. You speak. So with that, we're ready to go. So here's Felix.
Okay, thank you, Daniel. So yeah, my name is Felix. I'm technical lead architect at AMD and the kernel mode driver team for the GPU compute driver. So I just kind of threw these slides together yesterday. Like Daniel said, this was supposed to be a BOF. So the slides are more or less kind of an introduction to what we want to talk about and kind of keep the discussion focused on what we're trying to achieve here. So yeah, let's get started with that. So Daniel started talking about like the memory management, how we're changing the way we do memory management on the GPU, and then so the tool we're using here is it's HMM, the Heterogeneous Memory Manager. This is something that has been introduced a few years ago, originally by Jérôme Glisse, and has since been worked on by several people, including Christoph Hellwig, who has made lots of contributions to it, Jason Gunthorpe, who is the official HMM maintainer right now from Mellanox, and more people than I can really name here. So HMM was originally motivated by basically getting a better integration between the Linux page allocator and virtual memory manager and how devices manage their memory. GPU drivers had been doing kind of like a well, more or less broken way of trying to do the same thing with get user pages and MMU notifiers, basically trying to get system memory mapped into their GPU address spaces. Different drivers have implemented this in slightly different ways, and each of those implementations has been buggy in different ways. So I mean, there are lots of potential pitfalls with race conditions and lock dependency issues. I know Kristen and I have worked through a lot of those in the AMD GPU driver side for over the course of probably years. So HMM has kind of provided a toolbox to kind of unify a lot of that very complicated, very complex code and interaction with the memory manager, and then provided the tools for driver to kind of achieve that in a clean way and with hopefully as little bugs and race conditions and intermittent issues as possible. It also has added new functionality that was not really previously possible. So we have the zone device where we can represent device memory pages in VMAs. So they are part of the regular anonymous or fileback memory maps in a process, and kind of integrates device memory with a shared virtual address space in that way. And at the same time provides the ability to migrate memory into device memory to provide the best possible performance without losing that shared virtual memory kind of capability. There is documentation for this in the kernel documentation, which currently is mostly written for driver developers. And that's one of the challenges I think we want to address in this session here. So let me move on. So what motivated originally the BOF and then now this session here in the GPU memory management microconference was a patch series that we submitted for basically adding device public memory to HMM, or basically some ability to have coherently CPU visible device memory integrated into HMM and have the ability to have that mapped in the CPU side and migrated to the device at the same time. There were a number of questions raised in that code review that are seemingly quite fundamental to how HMM works. And so I think there might be a need for more documentation of HMM, not geared towards the driver developers, but geared towards other subsystems in the kernel that now willingly or unwillingly interact with device memory through HMM. So some of the questions that were raised here is, should the zone device pages be classified as PFN valid? How does page locking
Sorry,
work?
Felix. Like, don't these already have pretty well understood answers?
Maybe they do, but nevertheless, those questions were raised on the code review by people who I thought should know this stuff and tell me how this works rather than me telling them. So I think this is worth discussing here and maybe documenting.
So my understanding of PFN, PFN valid, I don't know. There was a big thread about PFN valid recently, and I think it came down to it means there's a struct page.
Right, that was my understanding too.
Yeah, I think what I suspect is that Christoph had some idea about how to repurpose PFN valid to do some new work and simplify the API, and he never did elaborate on that.
Does PageLock guarantee exclusive access to zone device pages? I think the answer is just no, because they can be in forks and things, right? Shared memory. How does the FSO?
Yeah, so
What do you mean by exclusive access? Are you talking about the contents of memory? Are you talking about the metadata that's in the struct page?
I was probably thinking of the metadata, and I think most of the page locking is really done by the migration helpers, so I don't think there's too much interaction with the drivers. I think we provide locked pages as one point, and then the migration helpers take over from there. So as I understand it, I don't think it's a problem. I think the semantics of how the page metadata is managed is not that different for zone device than it is for other pages. But I mean, hey, that's up for discussion. So let's see if someone else knows more than me.
Well, I think the problem is that the zone device work was just shoveled in without any real understanding of what it does by anyone in the MM side of things.
And it didn't help that it was all kind of done weirdly, like the page ref counts all messed up, like you're trying to fix with Ralph.
Yes.
Yeah, we keep running into it. Like there's this other thread with Zhao about the dev map stuff and get user pages. Like, what the heck is that for? Apparently, it's not needed. It's covering up a security bug or something.
okay, so that's what we're here for. And
hang on, Daniel. So I think the fundamental problem is that HMM tied its wagon to DAX. And that was the fundamental mistake, because as far as I can tell, the two things really have very, very little in common. And so whenever you're trying to do something that works for HMM, you end up having to think about, well, what does DAX need? And vice versa. And so I think the thing we can do that will be most helpful is splitting apart DAX and HMM.
Are you confident that they don't need exactly the same thing?
Well, when I talked to Jerome last about this, he failed to convince me that DAX and HMM needed the same things. Now, clearly he then talked to Dan Williams and managed to convince Dan that DAX and HMM needed exactly the same things, but they sounded entirely different to me.
My understanding of DAX is quite limited, so I couldn't convince you either. But just looking at the code, like I don't see a strong significant divergence. Like zone device is all about giving a struct page that's not CPU memory. And that's kind of where DAX falls. That's where HMM falls. That's where that weird P2P thing falls.
Actually, no. DAX, persistent memory is CPU memory. It's on the DRAM bus. it is directly addressable by the CPU at all times.
Then why is it so special? Why is it special in every way? Why does it have special ref counting? Why does it have special is DAX tests everywhere?
So I think the only thing that's really special about DAX memory is that when you try to gup it, you don't want to bump the ref count on it. You want to bump the ref count on the thing that owns it.
No, when you gup the DAX memory, you get blocked from doing long-term gups. I think that's the only special thing there. But the gup behavior of all these subtypes of zone device is all different. Like if you gup device public or device private page, I would expect it to migrate it to CPU memory.
Device public should not get migrated because that's CPU accessible to where it is. That's
No, wait, didn't we delete device public or something?
It was deleted. We're trying to add it back. I mean, the
Okay.
CAD series that's under review right now, originally we were trying to kind of repurpose device generic for what we want to do. And we're convinced to instead add back the device public because it's sufficiently different from device generic.
There's our expert.
My ears are burning on my mobile, so I just ran back upstairs.
Can you tell us if DAX is the same as GPU memory?
No, not even the same universe. Like Jerome latched on to zone device because I got pages, and that was where the similarities ended immediately there, because DAX is about memory that has no business being touched by the page allocator, has no coordination with the core MM. It's independent. It's just there for get user pages. And HMM use cases, we don't want get user pages. We want to work with the page allocator. We want to be tightly integrated with process and memory management. So the only thing they have in common is struct page, which is like the entire kernel. So it was just a way to add struct page at random places, and that's where the entanglement ended, in my view.
But do we benefit by having a zone DAX and a zone not DAX?
I don't think. I mean,
Like we have the zone subtype already.
Yeah,
we don't really have enough zone types is the problem.
Yeah. I don't think we help ourselves by adding more zones, like and the zone device snuck in, and then wasn't kicked out. But yeah, I mean, because it takes up bits in the page metadata for like where does this page go, and we're already kind of trying to there's pressure on that space because that's where we put our node numbers too, and so NUMA node numbers are getting more precious because people want to use NUMA node numbers to describe memory types. So if we increase our zone types, we squish our NUMA node numbers. I'm not sure we want to go there either.
So I mein, maybe zone device is actually a way to plug in all that weird infrastructure under another multiplexer.
Yeah. I mean, I think zone device should is the starting point to branch out to other things. I think it's super useful to be able to describe things with struct page only because of the legacy. Like I think if we can get rid of struct page, great, but we haven't been able to get rid of it. So as long as struct page is there, I think we need something like zone device to say, hey, there's some other way to tell the kernel about pages that's not the system memory map. That there's pages that devices discover and tell the kernel about. I think that's a useful mechanism. But then how to do the differentiation? Like it's leaked into all kinds of problems with like the memory failure path says, if this zone device page happens to be a DAX page, we know how to do the memory failure. For HMM, we have no idea how to do it, so we punt.
But that seems like an abstraction breakdown. Like if zone device is supposed to be a place to plug in all this stuff, DAX should not have gone in and just put DAX, if DAX in the memory failure, it should have plumbed it through zone device so that the other providers can provide memory failure semantics.
Plumb it through zone device means all zone devices is PFM.
I mean, have an actual abstraction that it could be plumbed through, like an ops table for the different subtypes or something.
Maybe. I mean, yeah, like so we're actually going the other way now. File systems want to be involved in memory management, and so it's not like we could push things down into zone device. We have to push things up into the people that are who might be owning that PFN at this point in time, because that's mainly DAX problem, because DAX punched through PFNs to sectors to storage, so a lot of things got a lot of abstractions got taken away because we don't have an indirection for that kind of stuff. But I mean, I take your point. I think the only reason punted on memory failure for HMM was just total lack of any knowledge about how memory failure handling would work for a GPU side of it. So I was kind of hoping for the HMM people to help.
It has to be plumbed down to the driver that's providing the physical memory has to implement all of this weird stuff, right? That's why, like I say, like ISDAX is not helpful. You need to plumb it down to the driver that's actually created the zone device in the first place. And that's what kind of I would have envisioned as a zone device API being in the MM. Is it a way for the driver to plug into the kernel's MM and customize all these special things that we have? And so to answer to answer Matt's sort of challenge is it the same as DAX? And that's where I, very hand wavy come to is it, yeah, it's a way to plug into different places, and we should try and make them more the same by making an abstraction layer here rather than having ISDAX everywhere and then throwing our hands up and saying, I don't know what HMM is all about. HMM is, you call the GPU driver, and the GPU driver, each one is going to be different, and they have to figure out what to do in these special cases. But right now, I think they don't even know what the cases are that they need to do.
Yeah, I think the ISDAX sprinkling is not what we want. We want more ops handlers and saying, I am the owner of this PFN. I need to get called back when something happens, which is what we're doing now for memory failure handling. Is the memory failure now, instead of trying to have a common memory failure with a bunch of ISDAX in it, actually just has an operation instructor that says, hey, is whoever owns this PFN, do you know how to handle memory failure? And we call that callback, and then that callback says, hey, do you actually file system? Right now we're building up a chain of memory failure talks to the PMEM driver, talks to the file system to pass these operations of anybody who. So it's like a notifier, but it's just more explicit. But yeah, I think I agree with you that we need more of that. Pretty much everywhere there's an ISDAX is probably a place where a upper level software has a better idea of what to do with it.
When you're talking about memory failures, you're talking about things like MCE events?
Yes.
Yeah.
Okay. Because I mean, if you're talking about device memory coming from a GPU, for example, I don't think you would get MCE events for those. I mean, if the GPU supports ECC, that event would be detected by the GPU driver first, and then maybe handed up the other way.
When we're talking about high availability enterprise systems, you could get an MCE because your PCI link died in the middle of a CPU read, right?
Okay, so it's not a problem with the memory itself, but with the bus in that case. All right.
It's the whole architecture. Any point where you could get it for an AER too, like any point where the CPU is stalled on a read or something, and the underlying everything can't provide data there. You should really trigger an MCE, and you should really recover the CPU and try and keep going. That's what enterprise RAS is all about. And ECC on the GPU doesn't excuse you. You could still have a double bit failure on your GPU or a chip failure, whatever the granularity is, and you still have to bubble that all the way up and recover the CPU that's now blocked on that read.
And the memory failure core routine gets called in both that synchronous case of like I am handling a machine check right now, and the asynchronous case of my platform firmware or my BMC or some other agent said, by the way, this PFN that you might access in the future is bad now. So I would expect that for HMM, that if the GPU experienced some problem, like the page went bad on the GPU side, that it would somehow tell memory failure. So memory failure can offline the page or migrate it or do whatever it needs to do to make sure that page doesn't get accessed again if it can't be repaired.
Yeah, I mean, the reality is probably GPU world isn't there yet. Like they don't care about that kind of RAS level
No, we
compute
do actually.
clusters.
We
Well,
do have RAS on our data centers GPUs, and I wasn't thinking of the interactions with the CPU side. I was thinking more of the GPU side, where the GPU detects the ECC error and handles it inside the GPU driver, and the CPU might never find out. But yeah, I mean, if you're right, if that memory gets accessed by the CPU, and the CPU access is failing, then I guess that's relevant on that side as well.
So we've been talking a lot about having operations vectors for various things, and we already have one of those for pages, right? It's page mapping AOPS. So is there anything we'll be talking about that can't be handled through that? I mean, you know, maybe there isn't an AOP, a specific AOP for the thing we want to do, but in concept, could we add those things there?
At least for at least for mappings, the problem is that the mapping is a one-to-one relationship, and file systems want to make that a one-to-n for RepLink. So mapping is hard, or mapping is contended.
But all the mappings would have the same AOPS, right? Because the only time the file system would have set different AOPS is like if the page is part of a directory on one hand and part of a file on a different hand, and that's not going to happen for the same page, right? It's going to be two files, so it's always going to be the same AOPS, even if there might be two mappings that want to talk to it.
do we have AOPS? Isn't that kind of a high level? Are you talking about the PG map AOPS or sorry, ops or?
I'm talking about address space operations that you'd
Oh,
find in include linuxfs.h.
I don't think that matches what they're trying to do here. They want to take like a chunk of anonymous memory and just drop in a zone device page through migration, and it's still an anonymous VMA, so the FOPs are still, and the address space is still wherever it came from.
Well, that's interesting. I didn't realize that for the HMM use case, you actually talk about anonymous memory.
Yeah, I mean, we'll be interested in doing file-back memory in the future as well, but currently I think it only really supports anonymous memory for migration.
Yeah, that's where they really are completely different between DAX and what this stuff is all about. Is that this stuff is about taking anonymous memory and turning it into device memory and then allowing it to kind of flop back and forth depending on demand. And DAX is all about starting with device memory and just keeping it as device memory.
The more I learn, the more I think, no, I was right the first time. These two things are entirely different.
Yes,
Well,
the similarity is they're plugging in device memory into the system. Right.
We probably do want to get file back memory worked into this, but not necessarily in the immediate patch set. That would be kind of a steep uphill climb. But yeah, we should have that discussion and figure out, how you're going to be able to mem map this GPU memory. That's a real thing, and there's already some existing examples of that. They just don't work, all that well. They work, but there are performance issues and so on.
I think there's still a fundamental difference between DAX and HMM in the sense that with DAX, the device memory is the actual storage location, whereas with HMM, the device memory would be the page cache, right?
The device memory is the device memory, right? It's still,
well, no, but I
it's
mean,
never
you're
another
using device memory to basically as the page cache location of your.
You've gone into FS land, and I don't know if any of us are prepared to talk about FS land until we get.
Okay, and I admit I don't know much about it myself, but I'm kind of trying to see the fundamental difference, right? I mean, with DAX, you're trying to get direct access to the storage device on the CPU, whereas with HMM, if we are starting to do HMM with file-back memory, I think we want the page cache to migrate to device memory.
The difference is the locus of control. In DAX, the file system is in control. It knows everything that's going on. It's built on top of DAX. In what you're talking about, the file system's locus of control has been co-opted, and you've gone in and taken stuff that logically owned by the file system in the page cache and just changed it to something else. And that's where you're going to get into all the resistance. That's exactly what Dave Chinner was complaining about. You need some kind of protocol where you can go to the file system and say, hey, I want you to rebalance your page cache in this special way, and the file system needs to kind of be cognizant of this happening to it. Especially since it has very specific things like the dirty bit no longer works, and you can no longer write protect a page once you've done this. It's like a huge mess.
Yeah, I mean, that's kind of a question I had. I mean, how does this even work, like ignoring all of the migration stuff? Today with HMM, we can map a fallback page into the device address space with the HMM Mirror
Yes.
API. And
Yes, you
how does
can.
the dirty tracking work there?
It's done with MMU notifiers. So the file system triggers basically a write protect on the pages at a certain point in its life cycle. The write protect flows through to the MMU notifiers, which is supposed to trigger the device to do another HMM range vault, and then write protect the pages on the device. At that point, the file system is in control of the page, is guaranteed to be data stable because every element in the system has write protected it, and then it goes on to do what it normally does.
Okay. Yeah, and I guess you could do the same thing if the data was migrated to device memory, right? Like there would still be an MMU notifier because it's still part of the virtual address space, right?
Yeah. Yeah.
And if you try to get user pages, if the process decides to it gets migrated back. That's a migration event.
It's supposed to be, but we'd also like it not to be. That's kind of the other piece of this. So like when I said in the chat, let's stop talking about HMM. It's kind of true because there's a lot of different facets here. So you've got what Felix and Daniel are talking about right now is migration of anonymous memory to zone device pages on a coherent GPU. Right, that's a very narrow facet. When we talk about HMM range fault, we talk about synchronizing a off CPU page table with the CPU page table. Right, when we talk about fileback stuff, it's yet another different thing. When we talk about zone device and public, private, and all this other stuff, it's yet another different thing. When you go into get user pages land, how that interacts with this mess is when you get user pages, one of these special page types for DMA, let's say, you don't really want to copy it back to the CPU. You want to do DMA in place where it is right now.
Right,
And
precisely. And we do want to go there. We do want to sort that mess out, but can we do that like after 5.16 closes?
Oh yeah. No, like this is why I say it's important to disambiguate all these pieces,
right,
because you're only talking about this little chunk, migration of anonymous memory to zone device coherent pages. That's one very constrained thing. If you start to say HMM, it brings in all of this other mess that hasn't been sorted out.
Yeah, and maybe that's part of what's kind of holding up this code review, because like, there's just so many questions raised that are not directly relevant for the code under review, but they're kind of scaring the people who are supposed to review it.
Yeah,
right. We have to have a clear position on that, and something of a plan.
Right, because all these questions you've got here are not the one piece that you're talking about, because you have good answers for most of this stuff. Like, how does IO to from zone device pages work? The answer is it doesn't. It migrates to CPU memory when you do any action that triggers IO. Done.
That's the story for device private. It's not what we want for device public, right? Device
I know
public,
it's not what you want, but that's what you have now. So as far as
but I mean,
migration
part of the patch
goes,
series, part of the patch, like the purpose of the patch series is to introduce device public memory that can be migrated to device memory but remain mapped in the CPU page table.
You
So
still can't use get user private on that, right? You still can't use get user pages on that kind of memory.
I think that's okay.
And that's what I said. The answer is you don't get to do IO from these special pages because
I see. Okay, because IO implies get user pages. All right.
Because it implies get user pages, and until you figure that mess out, you're stuck. Right.
Okay. Unless your IO comes from a driver that also supports HMM, right? Then it would go
No,
to
you've
the,
said HMM again, so you've gone into the bucket of nastiness.
well,
There is a path that's not too
I-
terrible to enable HMM range fault to return DMA-able memory that's not in the CPU page table or any other combination thereof. So drivers using HMM range fault have some sort of reasonable shot at doing something here.
yeah, I'm thinking of the interaction of device public memory with HMM range fault.
Well, any of the special memory types with HMM range fault, there are options, and they're all kind of the same. We would like to be able to return a DMA address from HMM range fault that's usable by the device that's doing the import and deal with the mess that causes on the exporter side.
Well, the thing is, that is a lot easier with the device public memory we have in mind, because we don't need a
I don't
DMA
know.
address effectively.
Yeah, okay. Yeah, sure. If you're, yeah, that's great then. Then you can just change HMM range fault to return that memory type as a PFN.
Yeah. So I'll take another note for that.
The Matthew's question about the device private public thing came in with HMM when Jerome was saying like, oh well, this is public means that the CPU can access it. Private means that only the GPU can access it.
I think it's a little bit more than that. When a device private page, when you install it in a PTE, a CPU PTE, it can never be. There's no memory there. It's just a swap PTE. That's kind of the main distinction. When you get down to nuts and bolts, when you install a device private page, it goes in as a swap PTE. So the CPU can never ever touch because there's no memory behind it. There's no PFN behind it. A device public page gets installed like a DAX page. It gets installed as a dev map, right? So it has a real PFN. It has coherent CPU access like DAX does. The distinction becomes more relevant when you get into the HMM range fault and get user pages world. As Felix points out, we can't do anything with the swap entry except maybe call out to some kind of driver function. But when we get to a PTE with a zone device public, then we can just return the PFN because it's CPU memory and the importer can DMA map it and consume it like normal. So it's pretty good.
Yep. So I was sort of assuming that once we have device public, that the HMM range fault and the get user pages would be handled automatically. It sounds like
Not
there might
get
be
user
some more work
pages.
necessary.
Not get user pages.
Right, okay.
You can do HMM range fault, but you can't
Right.
do get user pages. The reason you can't do get user pages is that the operating model of the GPU is going to assume that it can migrate at any time that memory to and from GPU pages. And depending on exactly what your GPU has done, there may be conditions where the migration is mandatory. Get user pages requires the memory to be pinned and immovable. It's like the interaction of, it's like zone movable versus everything else. Like get user pages cannot return zone immovable memory.
Okay.
Yeah, this was always the problem with the problem with public was like look, it works except what if you do this? Oh, you can't do that. What do you mean you can't do that? like no, if public can't support it, then public can't exist. That's why public got ripped out.
But the get user pages is, we've got a lot of memory types now that don't work with get user pages. Zone movable, the DAX stuff, the list seems to just keep growing, which is bad for people doing I/O, but it's the reality.
Zone movable doesn't work with get user pages?
No, not for long term.
Not for long term. Oh yeah, for long term. Yeah, I mean, even long term is like long term is basically this is a to do that this is broken. Like, long term causes problems for everybody. But actually, I don't want to go there because that's a whole nother. We had a shouting match about this like 2 years ago. So never mind. I retract my statement about it.
Yeah, but there's an issue with get user pages. There has been for a long time. So we're touching on it. We should touch on it more, but let's not get blocked by it.
No, that's why I say you just don't get it. Just get user pages doesn't work for your stuff, and you have an easy path forward, and then come back later with some proposal about how can you marry these things.
Okay.
Yeah, I can see Matthew sitting there and wanting to have a proposal about that, but
No,
Let's see how that
I want to say something about zone movable. It's not relevant to this conversation, so let's let that drop.
Okay. It's going to be an interesting discussion when it opens, but I hope it doesn't open in the middle of the HMM patch set.
This is a minefield, as you've noticed, and so you have to be very specific about exactly what you want and have good answers about the things that don't work and how those things that don't work aren't usable regression.
Or don't matter, and focus on the thing that you're doing, just the narrow little thing that you're doing. Don't just say, oh, I'm going to fix everything with HMM. It's too ambitious. I think that's what Jerome ran into. It's too ambitious. You need to have little narrow things. Like we deleted most of what HMM, most of the stuff that was labeled HMM has been deleted from the code. The only thing left is HMM range fault, and Christoph has suggested we should delete the HMM from that name and call it something else. The only reason it hasn't been done is nobody's figured out what the something else is.
Yeah, there's no such thing as device public memory. It doesn't exist. So come with a different name.
It was deleted because no one used it, and because no one used it, no one knew what it was. So we deleted all of it when we did the HMM cleanup. At the same time, we deleted all the other HMM stuff.
Well, like I said, we're trying to add it back.
So you might pick, like Dan is suggesting, you might pick a better name than device public.
Yeah,
okay.
Pick something that's very narrowly focused, like because device public came and went and died. And if you say we want to bring back this thing that everybody had no idea what it was, then you're gonna spend all your time describing how this new thing is not that, and just like pick another name, and precisely describe exactly what you want and then why it can fit in and why it's not device public.
Okay, then I don't know. Maybe defining a feature would be that it's coherent. So call it device coherent.
Yeah. So and Dan, did you have a specific name in mind?
Oh no. I like to complain about the shed color. I don't pick the paint. I just reserve the right to not like the color after you pick it.
Okay. So the tentative name is device coherent, and we can improve it from there.
Device coherent sounds reasonable.
Yeah. Or device CPU memory or device, something that implies the CPU is involved. And private is all about there's no CPU mapping. And,
right.
Adding a few little comments around those little enums that explain very crisply, like what the actual code difference is, would be a good idea. When we're talking
crisp
about
comments.
Yeah, like what I said, device private means the CPU is a swap PTE. And it's kind of obvious once you read and digest everything, but from Matthew's perspective, where he's just drive by trying to understand this stuff, it's not obvious.
Yeah. Now we're touching on Dave Chinner's ask here, some actual documentation for the model.
Yeah, I mean, it could be a document, it could be comments in the code. I'm not sure what the right answer is. But I think there is a general issue that's like emphasized by the discussion we're having right now, that a lot of the file system and memory management people don't really know what's going on, and so it has to be documented somewhere.
And we haven't since forever, so that is kind of an ongoing thing. Fixing get user pages and having all this stuff work coherently, that's a challenge that we should address. We should identify that. Maybe that's next year's summit topic.
We've had a summit talking on get user pages and peer-to-peer DMA every year for the last 5 years. And
why break the tradition?
Why break the tradition? Exactly. We should keep going. Nobody should solve anything. That's how these things work. But I feel like we're getting dangerously close. Well, I feel like we're getting dangerously close to being able to fix something, because the thing that has been missing for the last about 2 years is someone on the GPU side that wants to implement. Right? We have half the solution. Like, we have the RDMA side kind of sorted out, and we don't have anyone on the GPU side that's been willing to implement all the HMM pieces, do the zone device stuff, have the special memory types. So without that, there was no way to go forward. If you guys get your special memory types in and become the GPU side, then we can figure out how to bridge the two drivers together and with actual patches. But until there was both sides of the bridge, you can't build half a bridge. That's what Jerome tried to do. He tried to build half a bridge in the kernel, and it all got deleted in the end. So
well.
So I wanted to talk about one of the things that Felix put up on this slide. You said GPU page tables can handle huge pages, 2 meg and 1 gig. Are there other sizes that GPUs might be interested in handling, like 64 kilobytes or something intermediate?
I guess different GPUs can have different page table layouts, and even on our side, we've been discussing different page table layouts to optimize TLB performance and stuff like that. I mean, 2 megabyte and 1 gigabyte is what our GPUs do right now. There could be other GPUs that do different things. Also, we have some fragment handling that deals with TLBs, but that isn't really concerned with the page table layout. But my point is, I think we want to avoid unnecessarily splitting and then rejoining huge pages when we do the migration to the device, because yeah, I don't think that's necessary.
Why do you see migrations fail? Like, what does that mean?
I'm not sure exactly what's happening. I've seen cases where migrations of some pages fails mysteriously, and I'm not really sure I understand all the conditions that are in the migration helpers dealing with that. I think it had something to do with huge pages, but I could have misread it. I'm wondering if someone knows something, like is there any known limitations for migrating huge pages right now, or I don't know. It's something we need to look into.
You think it's migrating back? It thought it needed a huge page and couldn't get one?
It was a migration to the GPU, something that was presumably already a huge page on the CPU side.
But doesn't the same problem exist on the GPU side? You could be going to the GPU and you couldn't get a huge page, so you'll have to fragment, and maybe that doesn't work.
Maybe, but that's not what I was seeing. It wasn't a problem with the allocation on the GPU side. It was a problem with the migration helper collecting the CPU page.
Oh, isn't there a weird sort of sketchy racy thing in there where the pages can be split outside the mmap block or some nonsense, and then it triggers some weird stuff? Maybe there's a little bug in that handling.
Okay, could be.
Hopefully it will not just be the AMD HMM team chasing these bugs in future. I mean, I'm not saying we should put in intentionally buggy stuff, but there is the community.
Yeah, and I want to point out that the community has been doing a lot of work on the HMM side, more than we have actually. So
yeah,
I think we should acknowledge that.
Great. And for me, the benchmark is when John Corbett starts writing up the details. That's when the bug is being hunted.
So the second one here, replication of shared read-only pages on multiple devices. I saw a thread from someone else that wanted to do this for NUMA localities within a process, and Linus shot it down pretty hard. I wouldn't bring that up, let's say, in your trying to get your very narrow thing merged. Maybe.
Yeah. What was that specifically?
I don't remember the thread. I just saw it go by and kind of read and thought, oh, that's interesting. But it was exactly this concept that you can duplicate like glibc, like in a NUMA context. Forget GPUs. It would make perfect sense to have your glibc pages duplicated on the NUMA nodes, so that every NUMA node is doing cache local access or DRAM local access of glibc.
So what we've found is there is a certain CPU, which I shall not name, that is very, very bad about instruction caches across NUMA nodes. So it has, let's just say it has weak caching, particularly for iCache. And so what people are looking to do is replicate text pages between different NUMA nodes. So if you want to do it properly, you actually need to have completely separate page tables for different threads running accessing the same code. What you can do to kind of simulate that is to map the same. It's to actually copy the code. So I mean, there's a bunch of different ways to copy the code, right? You can do essentially a supercal, where you not copy on write, but copy on fault, where you say, okay, I'm willing to sacrifice basically any amount of DRAM for this, and so anytime that I'll map this and then copy it out of the page cache into a local to this NUMA node allocated page on every fault. And so you map the, let's say you've got 4 NUMA nodes, you map the library 4 times, and then if you're on node 0, you access 1. If you're node 1, you access you do your fix-ups in such a way that you end up branching to a completely different location in memory that you've arranged is going to be on your local node.
How does that work?
Well, the same way the cow does.
God. Well, no, you said you have multiple copies, so you actually want the instructions, the instruction pointers, and the different CPUs to be pointing at different addresses, even though they're running in the same function.
So, I mean, you do it like you do it all in the linker, because you already have when you make a function call to a library, it doesn't.
It goes through the PLT, but
PLT, you're right.
The PLT is global too, so you need to.
I admit I didn't delve into that part of it. I was just assured that it worked, and they only wanted it for libraries. They didn't need it for the main program text, and I said okay because I don't like to know how linkers work. That doesn't make me happy.
Sounds scary, but so maybe something like that would work here. And just the other thing on this list, the P2P HM clients, I think that's straightforward. Just let the pages go through. They're blocked. Just let them go through. No problem.
No, for device private, I think you do need.
Oh, sorry, for device private. Yes, for device private. So what I was kind of thinking about would be reasonable here is if we could have a way to link a callback, perhaps through PageMap or some other thing, so that when HMM hits the private page and it knows it's doing a DMA map and a whole bunch of other stuff, it could then call the callback, and the callback could return the DMA adder T, and then everything can work out for you. Again, this is one of these things where we could try to make patches to do this if there was somebody on the other side, and the only people I think are using device private right now is Nouveau, and does the AMD driver use it? I don't remember.
Yes.
So maybe we should try to actually popularize this simple thing first so that we can address that hard thing. And other thing I wanted to throw in there is that kind of callback is maybe a way to go at fixing get user pages, or maybe that's I'm just opening a can of worms there.
So let's small steps, right? So if you have a driver that could do a DMA map for device private page, if the AMD driver is in that state, then yes, let's start talking about patches about how that would plumb through, how that would plumb through, so that we could make that work. Because that's straightforward. This is where Jerome had been driving at for a long time. We've had many debates about where to put the callback, but in the current arrangement, I would say put it in the PG map. And it's probably like, aside from the driver work to make the bar 1 mapping realize, or sorry, the GPU bar mapping realize, I think it's minor. Like it's probably 100 lines in the HMM file and maybe a couple lines in the RDMA side to fix that up.
I'm going to press you on details later.
Yeah, sure. Okay. The other sticky bit that keeps coming up, but I feel like Christoph has been worn down, is that he doesn't like DMA mapping bar memory.
Okay.
But everybody's been doing it anyway, and we've got like the Habana Labs driver that wants to do it now, and it's probably going to be merged. We've got the AMD drivers already doing it, and so forth. So I think he's just kind of
it's a whole new world.
Given up on that one, so I think we're okay. I don't know. I haven't heard a crisp opinion there, but anytime you do this, you're taking bar memory and you're putting in a DMA map and you're sending it to with the, exactly like Dan says, with the P2P stuff. Logan has a patch series that's working to clean that up that he just posted another version of. However, it has the underlying assumption that there will be zone device memory P2P pages backing all of this. So if that turns out to be the winning approach, then a GPU driver will have to create those zone pages for its bar. And when it has a device private page, it'll have to return the zone P2P page instead. And then it kind of works through naturally, which is another way to kind of approach this.
Okay, so a meta thing here is we're getting close to the end of the time, and I think the discussion is just getting going.
Yeah, a lot of the discussion is kind of the future stuff on this slide.
Yeah.
And some things, I mean, we spent a lot of
Exactly.
time talking about future stuff even before I got to the slide. Like I skipped over the slide for our immediate goals because I don't think we even have the right people in here who have been raising concerns on our code review.
Yeah. So what
I think we got some good. I think we got some good advice here. Renaming the device public to maybe a device coherent, adding comments in some strategic places to kind of help people understand what we're doing and then how this is all supposed to work.
Well, the other question to ask is what Matthew asked. Why is device public a zone device at all? And if you can define that and answer that, I think people will be a lot happier.
Okay, so that's exactly what we're going to do. And we're going to try and draw some big, bold lines around what we're trying to accomplish in this patch set and where we think it might go in the future, what we think is practical to do in the 5.16 timeframe.
Yep.
Yeah, you've still got another 11 minutes to
Yep.
cover the rest of the memory.
Yeah, I just saw it, saw the limit approaching, so I thought I'd flag that. So let's go right back into whatever seems interesting.
So Dan asks about the Newman node problem, and I know people have researched putting this on Newman nodes, and I don't know why they didn't like it, but I do know they didn't like it. I think the precursor system to Frontier used Newman nodes, if I remember correctly.
Yeah, I think if you're talking about NUMA nodes, are you talking about managing your device memory in the Linux page allocator, the buddy allocator?
The suggestion is you have a CPU-less NUMA node that represents the GPU, and you hang all of your GPU memory off of the CPU-less NUMA node, and then mumble, 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 something, something, something.
Okay, it sounds bad, but what was the specific reason that got shot down?
I don't remember. No, it didn't. It was done. If I remember properly, it was done on Summit.
Yeah, and then I think we did actually consider doing something like that for Frontier. And the concern was that you'll have the GPU driver competing with CPU NUMA code for the same memory. And we're just really too used to having the GPU driver manage the GPU memory, right? And I don't think we could wrap our heads around how this will work. Like HMM a couple of years ago was really just like a niche use case. I mean, it's becoming a lot more important now, but maybe as the memory model and the programming model evolves, this is becoming more feasible.
It still sounds like bad idea to repurpose NUMA. I think this has to be solved in the device memory model.
It kind of makes sense for some architectures. Like say if you have memory, if you have systems with gigantic GPUs and lots of GPU memory, like even maybe more than system memory, why would you want that memory go unused when you have an application that's not using the GPU, right? If that's just a NUMA node, you can allocate that with malloc from your CPU code, right?
This certainly is a kind of NUMA. That's not in doubt.
Yeah.
Does anyone know what the CXL guys are doing for their kind of byte addressable, almost as fast as memory devices, but that aren't actually memory devices? Are they keeping it on zone device? Are they putting on a NUMA node, or are they just mixing it with normal memory?
Anybody know?
I think Dan will answer in the
Dan is
chat.
the expert here, yeah.
Yeah, I hope he'll answer in the chat. He's listening. I think, but
Well, we can, that might be a good one to take offline. Okay, so I think we're pretty much done here. We could move on to chit chat, not related to HMM at all.
Yeah, or we have more time for questions. I mean,
Yeah,
this has been also a
question.
discussion between Jason and Matthew and us, and I don't know if the graphics people are just completely overwhelmed by the discussion, or if there are questions we can answer in the remaining 5 minutes or so.
Yeah. So anyone on the chat, and there are some 53 people in on the stream, is welcome to unmute and jump in. Otherwise, I'm going to let my camera point at my electric VTOL project here on the desk beside me. And that's actually going to get some GPU content in it, because my dream is to do some computational fluid dynamics simulation on my desktop as part of getting that that airplane flying. Okay, so that is our time for now. So I will officially declare an end to the mini conference. Does that work for you, Felix?
Yeah.
Thank you very much, Jason.
Yeah, thanks.
And
Felix,
Daniel.
Daniel, Jason, Dan, the
Matthew.
fourth Dan of today, Willie as well. Yeah, I learned a lot and have absolutely no input into any of what you've just said.
It's not like pictures, is it?
As soon as you said file systems, my eyes kind of glazed over, if I'm honest. I think that was when the sugar rush from the Lamington also really started tailing off.
Yeah, I have an ulterior motive in getting that file system stuff resolved, because I have this file system called Tux3 out there that I would like to get merged. It's still worth merging, and one of the blockers is exactly in this part. It's the interaction between actually RDMA and movable memory. So it's very much the same ballpark, and I intend to get into that, but definitely not in the context of this device memory migration.
Yeah, zone movable is definitely a lot closer to my heart, since I, usually end up playing in this size world, and CMA is a thing. So here we all are. Yeah.
Yeah,
Okay,
I was
so-
going on, and I started it with my speculation that this stuff is actually going to migrate down to devices that size. And I don't think that's facetious. I think we are actually going to see vision and AI applications at that scale that are using this kind of memory sharing.
I know a lot of the embedded devices that I'm familiar with, they just have coherent, a single pool of coherent memory. And so they don't have this problem, right? It's just all memory. It's all normal pages. There's no issue. You don't have, the issue that we're facing is effectively a distillation of the NUMA problem, just with a GPU instead of a CPU. And if you don't have NUMA because your system's so small, you don't have the problem in the first place.
Yeah, but those systems keep getting bigger even when they're small.
They do, but NUMA usually comes out when you have to have multiple dies. If you have single die, you can
Uh-huh.
often avoid the NUMA issues. I don't know if we'll see embedded with chiplets, multiple chiplets for the compute side, and I don't know. But
To be fair, no one can fab them anyway, so we bought ourselves a couple of years there.
What are you saying?
Cool. Right. Well, on that note, yeah, I guess a lot's going to follow up on Linux MM and DRI Devel and AMD graphics and all scattered over everywhere. If someone could please help fill in some of the shared notes, that would be super helpful.
And Matthew's now. Never mind.
Yeah, I was taking notes there. A lot of them are incomplete, but I can also go back and listen to the recorded stream again and flesh that out. I've also volunteered, perhaps foolishly, to attack the documentation issue. And as Felix says, that is something we can do in the code, because we can put metadata in the code that gets automatically translated into documents like the HMM document. So that is something I think we should do. And we can start with some like wrong documentations and let the brilliant minds out there turn it into right documentation.
If somebody wants an interesting task, it might be to build a proper KDoc for this set of APIs, like Matthew did for Xarray, where you have the kind of the pros about how it works and so forth, and then you have the KDoc linking to the actual functions, and you kind of organize it in a nice, and then get rid of
that's what I meant.
HM.RST.
I haven't got the terminology because I haven't tried it myself, but soon will.
Okay.
I've
I
never
had
tried
some
it
notes too. Daniel, I'm going to send you, Daniel Phillips, I'm going to send you what I have, and then maybe you can distill that with your notes.
Okay.
Thanks very much.
Thank you very much, Daniel and Jason, and
Everyone.
see you later, Felix.
Yep.
Okay, thanks a lot. And yeah, we've now got ourselves another 15 minutes to refill sugar levels or whatever. And then starting from 1/4 the hour, Jason Ekstrand's going to be taking us through our final talk. So enjoy. All right then, we're into our last however many seconds of the break.
So how do I present my slides?
I will give you the power. No, not like that. What was I done? Start. So you should now have a button down by mute to share your screen.
Aha, share my screen.
Yep, and while you do that, yep, welcome back into the last bit of the break. I spent the 15 minutes trying to think of a synchronization joke, and the best I can come up with is that all the memory management stuff paged it out of my brain. So with that, Jason, going to be talking about synchronization, why we have more sync objects than memory management has page tracking structures and arrays, and why all of them are useless to an extent. So yeah, you've got 45 minutes to sum up, I think, about 800 mails on DRI Devel, and good luck.
It's okay. I timed this talk and I can do it in 12, so we should have plenty of time for discussion. I can't sum everything up in 12, but I can go through the slides that fast. So first of all, some special blame. I should blame Daniel Stone for making me give this talk on very short notice. And I'm going to blame Daniel Vetter for agreeing with him and not stopping him. And yeah. So if things are a bit rough, I'm sorry. Why did I just get muted?
Yeah, there you are. Sorry.
Did you hear me before? Or was I muted then?
We lost you after blaming both Daniels.
Okay, so both Daniels are properly blamed. So let's talk about a little bit about the current status of GPU synchronization in Linux. So depending on what parts of the graphics stack you work on, you may have seen any or all of these different synchronization primitives. And this is not a complete list. The point of this slide is just to tell you that there are a killer of a lot of them, and they're everywhere. And every API seems to have a minimum of 3. Good news is that inside the kernel, everything here is struct DMA fence. With the single exception of XShem fence, but that's kind of its own beast. Basically, everything in the kernel is struct DMA fence in some way, shape, or form. Implicit synchronization is done through DMA reservation object, which is a container of struct DMA fence. Sync objects are a pointer to a struct DMA fence and a lock. Timeline sync objects are a struct DMA fence that happens to be a DMA fence chain, etc. Everything's a struct DMA fence. So for those of you who aren't extremely familiar with this, basically it's a structure which represents a potentially future event, has a Boolean signaled state, and a bunch of helpers to allow you to wait on it and things like that. There are 2 particular guarantees that we're concerned with for the purposes of this discussion. One is that it's one shot, i.e. Once you've signaled it, it's signaled forever for the lifetime of the object. And the other is we have this guarantee that they have to be signaled in finite time once they've been exposed. And exposed is kind of a hand-wavy thing because there's some fun stuff that you can do as long as you keep it inside your driver. But the moment you've given it to user space or given it to some other driver, you have to signal it in finite time. And this guarantee has a bunch of important implications. First of all, you can't have any circular dependencies because then you would deadlock. Nothing which is required for signaling one of these is allowed to fail. So that takes out a bunch of locks, and it means you're down to GP, no wait, and atomic if you want to allocate memory. If you're on a GPU and you have a hardware fault of any sort, the standard solution is you reset the chip, kill the user space, and signal all the associated fences. That way the fences at least signal even if the user space context dies. But these guarantees have the very, very nice upshot that you can wait on a struct DMA fence, not anywhere, but in a lot of places. So it can block swapping, it can block buffer migration, it can block the shrinker. Very, very useful. But the problem is that user space isn't happy with this. User space wants more control. So a couple of examples of this. AMD and Intel and ARM as well all have some sort of plans to sidestep the kernel. I'm not going to speak to AMD or ARM's plans, but Intel's plans run something along these lines. Basically, the kernel driver still manages memory and any sort of global resources. It tells the user space tells the kernel what resources it wants to be resident in memory at any given time and where to map them into its page tables. And then user space submits its batches directly to firmware without the kernel really knowing what's going on. In theory, this should be faster, lower latency, and all sorts of other good things. Like I said, AMD and ARM have similar plans. And Intel, we have a prototype of this we've been calling ULLS. We're using it in a compute driver today. It used to work on upstream, but then we had to kill it due to the fence issues we're talking about here. We have a non-upstream kernel branch where ULLS is being used with pretty good success. Another example of where things kind of fall apart is that high-performance clients want more of a timeline model. So this was the #1 feature request that we, i.e. Kronos, got for Vulkan early on. People were not happy with our semaphores and fences, and they wanted a timeline model. So we have this timeline semaphore extension, which basically gives them a sequence number thing. You have a 64-bit integer. To signal it, you set a higher value. To wait on it, you wait for the value to be greater than or equal to some target. And you can wait from the GPU or the CPU can signal from either. And this kind of replaces the old stuff that we had. This looks a lot like what we do inside drivers today. You know, you write a sequence number, you trigger an interrupt, and that's the way most of the synchronization works. It's also the same model that game developers are getting on D3D12. And I believe it's the same model they're getting on most of the consoles today as well. Game developers absolutely love it. One of the big reasons is it's a lot better for multi-threaded engines, and I could go into that, but I am not going to go into details there. They come with a few caveats, though. One of those caveats is that you have wait before signal. So client can submit some work that signals semaphore A to set it to value 7, and then later, but before that work actually gets even submitted, much less happens, it submits some other work to wait on it to hit timeline value 7, and we're responsible for sorting out the dependencies. Of course, if the client is allowed to specify arbitrary timeline values, it can deadlock. That's okay. Vulkan is perfectly fine with clients doing all sorts of nasty things to themselves, and that's just their fault. As long as the system stays standing, we don't care. We have an emulation of this for the AMD and Intel drivers that uses DRM sync object, but it is not really as efficient as we'd like it to be. It's not really the implementation we would like long term. The third example of where this kind of falls apart is that compute doesn't happen in finite time. So in 3D space, everything completes in less than a second typically, because your monitor refresh rate is 60 hertz or higher. There's a lot of stuff that's higher these days. Anything that runs below 20 hertz is unplayable. So, you know, most stuff does compute in a fairly short amount of time. In the compute world, this isn't at all true. The GPU is just another processor with a bunch of cores. Compute job could take forever. Why shouldn't a single shader run on the GPU for 3 days? So there's no real concept of finite time there anymore. Currently, the way this is dealt with is either drivers cheat behind the kernel's back and just don't do DMA fences somehow, or the jobs have to chop their work up into smaller pieces in order to avoid hang timers, or it just doesn't work properly. We don't really have a good solution for that yet, and that's part of why we're having this discussion. Okay, so what does the glorious future look like? My vision of the glorious future, personally, is what I'm calling user-space memory fences, which is basically copy and paste of timeline semaphores only in memory. So you have some bit of CPU mappable memory, and it's either 64 or 32 bits, depending on your needs. And signaling is done by writing to memory and signaling an interrupt, just like you would do for internal synchronization within your kernel driver. And this might happen as part of an ioctal, or user space might want to do this itself. I want to allow for that. CPU weights are similar to futex. I don't know that we can actually reuse futex, but some sort of an ioctal that waits on that bit of memory to change values to something useful. And then GPU weights, basically whatever your exact ioctal is, it takes this pointer and it takes target value and it waits. And that's your synchronization model. No more sync objects, no more implicit synchronization. Everything happens by just writing memory values and waiting on memory values. This would basically give us timeline semaphores exactly the way that they're intended to work. This is basically what Microsoft does with monitored fence. But it has a lot of problems. And there's a lot of other different models that have been discussed. There's long mail threads with AMD and Intel and a bunch of other people talking about a number of different models for user space controlled synchronization primitives, but they all fall flat because they all have the same problems. So I don't want to go over all the models because they all have the same problems, but this is the model that I'm working with personally and where I would like to see things go. So the actual future is a little more grim than what I've said would be beautiful and wonderful. Why? Well, the short version is that none of user space works this way. So all of user space uses all of these sync objects and sync files, and they all tie back to DMA fence. And DMA fence requires finite time, and we can't guarantee that with memory fences or with any sort of user space controlled fence. So why not wrap and instruct DMA fence? That's what I just said. Yeah, so we could wrap it and instruct DMA fence, and user space might just never bother to signal it, or might signal it wrong. Like if we're depending on writing memory and then firing an interrupt, it might forget the interrupt. User space might deadlock itself. Okay, so we can't trust user space, we know that. So let's throw a timeout on it. That should work, right? Well, the problem is that user space can't trust us either. So let's assume user space submits a bunch of jobs with an acyclic dependency graph. Everything should sort out as far as it's concerned. We as the kernel have absolutely no idea what that graph looks like. We have no visibility into it whatsoever. All we know is that user space probably has done something acyclic. And we might want to do something like, say, move memory. That's something that we do all the time. These operations add dependencies to this graph. The moment you add dependencies to an acyclic graph without understanding what the original graph is, you have the possibility of adding cycles. And then your cycle causes a deadlock, and this causes the fence to time out, and we kill the user space context. Awesome. We protected ourselves, and user space kept the pieces, except user space didn't do anything wrong in this scenario. And I think it's very easy to construct these scenarios. But the important thing is that user space does something that it thinks is 100% correct, and it gets killed because we added a dependency without understanding the graph. So how do we break this? The best solution that anybody has come up with so far is to separate memory and execution synchronization. So basically, you keep doing memory management with all the DMA fence stuff we have today. Kernel does dependency tracking with DMA fence. We use TTM, all of those useful things. It doesn't look that different. What looks different is that any sort of synchronization, execution synchronization, so user space to user space, that happens vis-a-vis user space fences. And the important thing is the kernel never waits on a user space fence. If the kernel ever needs to do something like, say, move memory, it preempts the context, all the contexts that are touching it. It knows that because we've told it what is resident and what isn't. Moves the memory and restores the context. As long as you preempt happens in finite time, you can block a DMA fence on it, so that's fine. This depends on preemption in order to work, but all the big GPUs, AMD, Intel, NVIDIA support preemption at these days at enough granularity that this is probably tractable. So we can implement this. And this is what we're doing effectively right now for ULLS. Well, not quite, but it's where we're headed. And we're pretty sure this is implementable and it works. Okay, so we should do that. this leads us to the interop problem. So one of the problems with this solution is that kernel can never wait on a user space memory fence. We can never turn one of these things into a DMA fence. And as I mentioned before, everything in the Windows system, everything that's any sort of client-to-client interop, OpenCL to OpenGL, anything with EGL, Wayland, X11, all depends on implicit sync files or something of that ilk. It all depends on DMA fence under the hood. So what are our options? Where I sit, what I've seen so far, we have basically 3 options. One, we can replumb absolutely everything. This includes all the kernel drivers need to separate memory and execution synchronization. We need a new user space facing synchronization primitive. We need all of our user space drivers to switch to this synchronization primitive. We need all of the distros to ship all of the new things, and we can build a new world. Option 2 is that we just wait in user space before passing it off to another process. This solves all our deadlock problems. When somebody does VKQ present to send it off to X11, we just sit there in a user space thread until the rendering is done, and then we hand it to X11. So it solves all the deadlock problems. We don't have any cross-process synchronization because we're just waiting in user space, but that also means that all the cross-process pipelining that we've spent so much effort to try and build is just gone. And it also totally breaks Wayland in a couple of corner cases. Option 3 is find somebody more clever than me who can come up with a better option. So that's the end of my very quick bullet train rundown. And I will open the floor to suggestions or objections or other comments.
Yeah, long story short, I've sent out a proposal for option number 3 roughly 6 months ago. But Daniel basically torn it apart as, okay, there's a lot of open ends and a lot of implementation needs to be done here. Basic idea is you can still wait inside the kernel, but not inside any shrinker callback or anything like that. Only in the top of the I/O control when the command submission comes in. Partly solves your problem, but not completely. No.
That sounds a lot like my wait in user space solution.
Exactly. It's basically the same as wait in user space. It just moves the wait a bit further to the command submission. The good news is you then don't wait on before you interrupt with the other application, but you then wait when the other application finally submits something to the kernel. And we could avoid that wait, or could, yeah, I think we could still make most of those wait solve up in itself. I have no idea how to explain that in English.
Yeah, I think so. To be clear, the first proposal was essentially, let's deal with this in the kernel by moving all this Windows system stuff down there. It's actually easier for us to rewrite all of our implementations than for that to happen.
Well, I think one complication that's maybe in the room here is, was maybe a bit lost, but I think we can't ignore it, that like we still have like one subsystem even for the tiny garbage GPUs. So I don't think we can ever get rid of DMA fence for sync, because there's going to continue. Like the big desktop GPUs, they're all going to have preemptive various varying levels of usefulness, and maybe page faults on the hardware side of varying levels of usefulness. But like the tiny ones, like realistically, I think the only sync you get there is end of indirect buffer. So I think that's another complication.
It
We need
depends
to keep
on-
that part working.
Depends on how you define tiny, though, because Mali Gen 10 scales down quite a long way, and they still have. We don't have the details yet, but
yeah,
it's pointing firmly in that direction, and that's going down into SBC. So beyond that, in terms of GPU, all you have is VeriSilicon, Vivante, who knows what they're doing, and also IMG, who have historically really closely kept up with Vulkan. So I can't imagine they'd be doing something which precluded doing timeline semaphores pretty efficiently. I think it's less about that and more about like you can't get rid of DMA fence ever, because no matter what the GPU, if it's a huge AMD or Intel discrete one, people are still going to try and run X11 on it. And who's, obviously I have opinions on that, right? But like, who's going to go rewrite Zorg?
Yeah. Well, so I mean, even if all the GPUs move there, there's the next thing coming up with all these AI thingies, and right now they very much look like GPUs from 20 years ago in some cases.
Yep.
So, like, people love to just chop these things off because, hey, who needs them?
Well, and even though we can't, even if you have a nice GPU in your system, we can't guarantee that you're not going to plug in some random USB display link device, which is going to have its own set of issues and throw a wrench in the works.
It's not a GPU, it's just a display pipe.
Yeah, but it still takes DMA buffs with DMA fences.
Yeah, exactly. I mean,
even a consumer can screw it up.
Yeah, basically, we have a combination of very old GPUs, very new GPUs, very old desktop environments like X11, very new desktop environments like Wayland, and all of them need to be working together. That's the situation we are into. So basically throwing anything of that part completely away and not have compatibility to it is not an option, in my opinion.
Yeah.
So, yeah.
Yeah, I do think probably the most realistic one is something like what Christian's done, or like some other way to carry around user memory fences in the existing container object, but probably with a lot more opt-inness, because I guess on the compositor side, you probably want to like deal with the user mode fences in the compositor, maybe. So, look, yeah.
Yeah, I don't think there's any way around that, and that's fine. We've got to do it, and we're already. No one's really thrilled that you can DOS your entire desktop right now just by passing at fences which don't complete until GPU reset kicks in. Like,
So,
that's a problem we've got to solve, full stop.
one of the other places where this all gets hairy is it's all well and good to say the compositors will figure out how to deal with it, but that means the driver needs to decide what it's going to use internally based off of what the compositor is able to deal with, or we just throw away all the old compositors. And in the Vulkan world, we create the device, we configure stuff. You can start
It's just a
rendering.
Vulkan bug.
No, it's not a Vulkan bug. Vulkan was designed properly. It's OpenGL and X that were designed backwards.
Everyone else is wrong.
But you can start rendering, and it's not until you actually go to present the first time that we know, oh crap, I have to be able to deal with DMA fences. And at that point, I can't swap my implementation out from under me.
I mean, wait a second. New drivers dealing with DMA fences is not much of a problem. The problem comes in when you have old stuff dealing with new user space fences, because you can always wait for a DMA fence, but you have a very limited point where you can wait for user fences. So when you have new hardware and when you have old hardware and new compositor, it will basically always work. But if you have new hardware and old components like old compositors or old X11, then we have a problem.
That much we all agree on.
So I guess the other thing is also when we stuff it into containers is like, given that implicit sync is like not very popular. I don't think we should like make implicit sync into a container for user made fences if we can at all avoid it. That sounds like complete horror.
There's another problem that we need to throw out here, which is it's all well and good to say we can go write new compositors. I'm happy to hear that, but most of us have to deal with Android, and Android is built ground up on sync file. And convincing Google to go rewrite Android sounds like a more challenging prospect.
Well, A, it's objectively easier than X11. B, well,
is that a scale we want to really put into the picture? Like, you know, here's all the reasonable things, and then there's maybe Google, and I can't even see X. Like, it's on the other continent.
Oh my God, you can tell it's getting into the European evening, right? But no, seriously, like, so X11 isn't a gigantic problem in and of itself. It's the implementation of Zorg, which is the really difficult bit. But yes, Android is built fundamentally around sync file, but that's a property of their implementation rather than something that's surfaced all the way through. So they do have the ability, like if they have the will, they have the ability to go break it. And you know, it's Mali and Snapdragon for them. So depending on what Qualcomm ends up doing with future hardware, they might be pushed to a point where they have to deal with it anyway, even though I'm pretty sure they have the option of throwing the thread under the bus on the client side, which we can't do on Wayland because that's what breaks the synchronization, where the client assumes it has one thread to send messages on, and that when you do VKQ present, certain things will get sent down the wire to Wayland, which is why we can't take that option. Android could. But yeah, the problem for generic Linux is more that we surface them as API forever. Like, I think that's the difficult bit, as opposed to Android, where it's a thing that the platform's built around, but the platform's much more mutable.
So I haven't started the DRI Devil thread on this, but I think the reason why Android gets away with all this is that they don't have memory management for GPU buffers. So their DMA fence is actually just the synchronization fence, which completely kills us because we have a DMA fence as an add fence on atomic commit. And I've recently, well, 1.5 years ago, or 1 year ago, I added a bunch of annotations, and it's unfixable. As in, like, as a display driver, there's just a bunch of locks you have to take from random other subsystems like I2C or whatever, and they happily do allocations underneath there. And in a pure Android world, you just don't care, because DMA fence is only ever a synchronization fence, never a memory fence.
Throwing a really bad straw man out there.
That's all we've got, so go for it.
Yeah, I thought I'd just join in. If we, assume that someone's going to buy an AMD GPU 10 years in the future and they still want to run Zorg on it, would it be the worst thing for... So they're still running the user space which is reliant on DMA fence. Would it be the worst thing for any CS? No, it can't be any CS which exports DMA fence. Any CS which depends on a DMA fence to block returning from the CS iOctal until that fence is retired. I mean, it's not going to be quick, but if you're using ancient user space on insanely modern hardware, then it'll probably still be fast enough.
I mean, that's essentially the plan, that we touch all the drivers who care, well, which pretty much means all of them, and do the same, like sync object has already to give me the sync object, and there's annotation in there to make sure you're not holding any locks so it doesn't deadlock. We essentially need to add the same for sync file. And if we really want to keep this working with implicit sync, which is just like a horror show, we have to do the same thing there, and I don't even have an idea how to do it. But then, then essentially, if you get a user made fence and you submit it to something old that does DMA fence, or end of command submission, batch buffer, IB, whatever you call it, DMA fence, then you just block before you grab locks. We'll block with a timeout probably. But that means like changing all the drivers, which also sounds like stupid.
You're breaking up a lot, Tristan.
Yeah, you're gone.
He's probably using X11.
Well, we're in position to come back. I did have a different, completely terrible idea for how to deal with X11. And that is that Present already uses XShemFence. You know where I'm going with this. Can we make XShemFence a wrap around a user space memory fence and signal it from the GPU? It means X will block on the GPU work before it sets up its blit, but maybe that's good enough.
Oh my god, I never considered that at all, because I spent 5 years raging at XShemFence for being useless and misconceived and everything that's wrong with everything, but just it was ahead of the curve.
Well, so honestly, the biggest thing about keeping existing stacks working, I think, is the implicit sync we have going on between everything. Like sometimes, mostly even in the same process. Like you grab an EGL image and throw it at Libya or whatever, or at compute. All these things. None of these APIs, as far as I know, pass around any kind of explicit stuff at all. So there's nothing we can attach to except we go and make DMA reservation and locking even more fun.
Well, most of the stuff like EGL,
I don't want to do that.
assumes some sort of a underlying shared EGL implementation, which we do have control over. Now, that control is entirely built on top of kernel implicit sharing, but we could, in theory, replumb EGL. I don't know how that works with libva and some of those other less EGL-friendly things. But we could, in theory, replumb a bunch of user space to do things differently. There's always going to be the random clients that know about DMA buff, export and import and do it themselves. And those we don't have a way to fix.
I mean, for the backwards compat, I mean, I think another option is if on like a per context level or whatever, we do a backwards compatibility mode. And I mean, that's, I think, essentially what AMD is currently aiming for with a bit of hardware help. But I think you don't even need a lot of hardware help, especially if you don't care about performance that much. So I think the entire backwards compat thing we can also solve with we run the driver stack in the DMA fence mode, except Jason insists that he can't decide which one he needs.
And I don't think that.
Oh, Koenig's dropped again.
Yeah, we lost him again.
Oh well.
I don't think that things like OpenGL, OpenCL, interop allow for that either. You don't start up OpenCL on a display. You start up your GL driver on a display, and then you do some magic calls and stuff happens. That extension is just horrible to start with. But your OpenCL driver starts up with absolutely no knowledge whatsoever about your Windows system, and then there are extensions to allow it to interoperate with GL using implicit sync because everything is EGL and awesome. And there's no way for the CL driver when it starts up to know that it's going to need to run in DMA fence mode.
Well, I mean, that's like we start up in user mode fence mode, and then any time you use an extension that is stupid and old, we punch out the entire thing underneath you.
Yeah, so CL, you can do that. You can just swap it. You can just flush everything, replace all your objects, switch over to a completely different implementation if you want to.
And if I remember CLGL interop right, I'll be pleased if I don't, to be honest. It's, you know, again, it doesn't give you all of the primitives. It's just you have two implementations, they're coherent somehow, you share some stuff, and then under the hood sharing occurs. So you could do the kind of opaque FD solution, right? By plumbing through there. I don't think there's anything in CLGL interop which literally requires DMA reservation.
No, you could share a socket if you wanted to and pass data back and forth.
Yeah, it's just it doesn't work like that right now.
Yeah, it doesn't work. This goes back to option 1 of replumbing all of user space.
So for the
slightly more contained, maybe.
For the Vulkan case, like, why can't we just punch out everything?
Because for one thing, they may have a bunch of pre-constructed objects, and we don't have a table of all semaphores ever created, for instance. We don't have that list, so we can't go and construct it. And we're strongly discouraged from taking locks all over the universe to maintain those lists. The bigger problem is that with timeline semaphores, we have no notion, even as the user space driver, when it's going to complete. So we can't flush everything out.
Oh, you can't just wait until it's like...
They've submitted stuff with some dependency graph. They might not have submitted the key to actually unlocking the whole thing yet. We don't know.
It might be.
Yeah, otherwise I was like, for the first problem, I think you could probably tackle it with some horror show called RCU in user space.
I've considered doing that.
I think that's like for the just the data structure punching out thing, like RCU in user space is a thing that's going to happen or has already happened, and I mean it's terrible, but yeah, it doesn't solve the entire. Oh, we've submitted half of our frame and the other frame is now stuck because we called the EGL export extension.
There is an option 4 or 5 I don't think ever discussed, which is to have quite a great deal of faith in humanity, hope that no one ever tries this new GPU ancient user space, and then the first one who complains about it gets to fix it.
I am actually fairly favorable to that in the sense that my primary concern is that all the standard stuff keeps working. Making something bulletproof that prevents any possible corner case, I don't think is a constraint we should put on ourselves.
Yeah,
but the ease with which you can construct horrible counterexamples using fairly reasonable looking combinations is quite annoying.
Well, the path to salvation starts over and the issue is that we change user space.
Christian, I think you need to type. Like you're a slideshow with Darth Vader overlay, and he's gone.
But yeah, I mean, Alex did float the exact same thing in the chat of minimum GPU requirements on compositors. Was followed by a winking face, but
I'm sympathetic to the argument. It's just that there are like one of the counterexamples that I came up with somewhere on that thread. All it required is a modern kernel driver and a USB display link device, which is a completely natural thing that people do all the time. It's called docking stations. And unless that display link driver is brought up to speed to be able to do all of the separate synchronization stuff, it just falls over. And like, yeah, if X11 is the only problem and my stupid XShem fence hack works, let's just do that. Like, we can solve that problem. But
I'm all for that. V4L2 doesn't participate at all in implicit fencing. I think VAPIs may be the difficult one in that they surface DMA buffs and have no concept of fencing. But yeah, if we can actually use XShem fence, and again, I can't believe this is an actual viable solution, then I think we're just left with things like, yeah, GLCL interop, sorry, the GL Vulkan interop extensions as well, to be fair.
GL Vulkan interop is solved. That uses you have to do semaphores from GL. So we can make the GL thing, as long as GL uses the user space fences, that's solved.
True. And yeah, also VAPI, where it's definitely not anything like intractable. It's just a bunch of horrible typing. Christian says we can't assume Android will ever be fixed.
I wanted to say that too. Well, raise Christian's base. On the Vulkan thing, just another like really stupid idea that just crossed my mind. Can we do a device lost?
Ooh, that's mean.
Well, so that's the mean part. But then we store in the shader cache or wherever, like somewhere nasty, that this user or this desktop or whatever is unfortunately stuck in like the last millennia and never ever gets again like the user mode fence mode by default. Or this application or something like that. So we just like we're sorry, we shot you. Oh, like, please reconstruct everything. And we make a note about like this exec or whatever. From here on out, like it unfortunately runs in DMA fence mode by default. So you die once on startup the first time when all the shaders are getting compiled anyway.
And if
And
your
Steam
stash
can
back
ship with
then-
these quirks like from the default on, right?
So it's mean and it's horrible and it makes more sense than it probably should.
Could it work? Like, I don't care about mean.
I mean that is going to have to be our final terrible suggestion because we are banging against the top of the hour and they're about to start the closing keynote. So on that bombshell, we'll have to leave it
My
here and drop
apologies.
out of this and continue on
And
DRI
go drink
develop for
ourselves
the
into
next
oblivion.
3 to 4 years, I'm sure. Yeah, thanks, Jason, Daniel, Christian, everyone else. Thanks for being here today, and to the organizers or the sponsors as well. Yeah, this will all continue on, and I'm sure we'll keep hearing more about it. Thank you very much.
Thanks to you too.
Cheers.